Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. We are finished with most of the physics that we were going to talk about, or the fundamentals of the physics and of stars and astronomy, and now we're going to actually delve into utilizing the physics that we were talking about in all the previous lectures to talk about stars, the galaxies, and the rest of the universe. It'll be a lot of fun. So let's begin at where most people do an astronomy class, the beginning with the sun. So the sun is the nearest star. So it's a really, really, really big object. It's the sun. It's huge. 1,000,000 Earths could fit inside it. 110 Earths can fit across it. And it's a big, big, big thing. It comprises 99% of all the mass in the solar system. And so studying the sun as a star is the best thing we can do because, well, all the other stars are really far away. They're on the order of parsecs away or light years away. That's trillions upon trillions of miles. So we're going to look at the sun as a star and try to understand it. So what we're looking at here is an enormous prominence that comes off of the sun. And these enormous prominences are gas clouds that are lifted in the magnetic field of the sun. And as they travel out into space, they can encounter the Earth and other planets. And they demonstrate that the sun is an extraordinarily active thing. So let's first now go through something I haven't done yet in this entire series. Let's give some questions about the nature of the sun and its properties. So you can go back through these, but I'll just read them really quick. How do you know that Alpha Centauri is a star that's nearly identical to the sun? There are clues inside of this lecture that are coming up. Okay, next thing, it's a math sort of problem. Assume that an airplane travels at 600 miles an hour. How long would it take you to go around the Earth, and how long would it take for you to go around the sun? So that's kind of a fun little thing. Try to figure that out. And if the sun is as big as the Earth, as you are as big as something, this is a compare and contrast. So big might mean volume, big might mean height or width or diameter. And so how big, so if you think of the sun as you are the sun, and then what would be something as small as the Earth compared to you if you were the sun? So now compare the mass of the sun to all the members of the solar system, individually and by groups and the entire thing. And the density. What is the density of the sun? Not numeric density. We could call it number density if we want, but that's going to be an odd one. But average mass density. Compare it to the air at sea level, the rocks that are typical for the Earth's crust, and typically the density of your body. And you're going to have to make some assumptions to figure out what the mass density of your body is. Yeah, make some assumptions and have some fun. Just figure out what they are. All right, and if you take a random sample of the sun and you see it as you find that it actually has the same chemical composition as a random sample on the Earth. But what are some of the differences? And how do we know that the sun's not a solid body? Compare the magnetic field of the sun to the magnetic field of the Earth and to a medical CAT scan device. That's interesting. Compare the surface temperature of the sun to boiling water, molten steel in a welder's arc. Those would be some fun things to Google and look up. And finally, how many gigawatts of power does the entire human race produce each year, and how does this compare to the sun's output every second? So you're going to have to Google that and look it up. It's a very interesting question. All right, so let's go on. The sun. The sun, we see at sunset. It is the thing that provides the light during the day. You feel its warmth at night, and it bathes the Earth as it orbits the sun. Which means that the light from the sun doesn't just hit the Earth, it goes out in every direction. The purpose of the sun is not to illuminate the Earth. The sun has no purpose in the solar system. It's just the biggest thing in the solar system, and the Earth orbits it. So the sun's light and the sun's heat and the sun's rays and its influence goes out in all directions. We just happen to intersect it in a very, very, very tiny amount, and we get very pretty sunsets. All right. This is a picture from Astronomy Picture of the Day by Max Alexander. This was the sunset at Stonehenge. And what's interesting about Stonehenge is it's an astronomical calendar tool. And that dates back a very, very, very long time. And it's wonderful to go see that. So to see the sun setting over Stonehenge, it's wonderful. So we've been thinking about the sun and what its influences are as many, many cultures throughout all of history. All right. So another thing then, if we go forward, Neil deGrasse Tyson at the Museum of Natural History noticed that twice a year the sun sets exactly down the streets of Manhattan and cuts across the avenues at 90-degree angles. So it sets directly between the buildings, and he coined the term Manhattanhenge. So if you go to amnh.org or just look up Neil deGrasse Tyson and Manhattanhenge, you'll find all sorts of stuff. It happens twice a year. And so this is a great time to be hit by cabs as they careen into the sunlight. So be very careful in the streets of New York and Manhattanhenge because the cabs can't see anything. They really can't. Anyway, so there are some there's some symbols and some things that we need to look at that are relevant to the physics of the sun. And we're going to be talking about the bulk properties of the sun. So each one of these symbols has a little circle as a subscript, and the subscript is a circle with a dot in it. And the circle with the dot in it is the alchemical or astrological symbol of the sun, and we just appropriate it because it's easier than writing out sun or the sun or solar or something like that. So the first one is a rho. It's not a P, it's a Greek letter rho, and the Greek letter rho sub sun, and that's what I'm going to call that circle with a target in it. Rho sub sun is the average mass density, or the mass density of the sun. It might be the average, it might be the surface density, it might be the core density. But in this case, we're going to call it the average density because it is the average mass of the sun, or the mass of the sun divided by the volume of the sun. And that'll be the mass density of the sun. The surface temperature of the sun, which is the capital T sub sun, will be the surface temperature that we associate with the photosphere of the sun. And that, or whatever, we might, or that's going to be our typical fiducial value, and we'll compare it to other things as well. M sub sun is the mass of the sun, and this will be useful all throughout the entire rest of all of astronomy. So we typically measure things in terms of solar masses. So the lower left capital M sub sun is incredibly important, and knowing that how much the mass of the sun is important. The radius of the sun also provides R sub sun, provides a fiducial value for a characteristic size of stars, and L sub sun is the luminosity of the sun, or the amount of energy it puts out in terms of light every second. So the luminosity of the sun in all wavelengths of light is what we call the L sub sun. So these are our bulk properties of the sun, and that's what we're going to be talking about. All right, what's the radius of the sun? Our sub-sun is 696,000 kilometers. And that's over 110 times the size of the Earth, which the Earth is about 6,371 kilometers. And so about 110 Earths fit across the sun, and if you multiply it out, about 1 million Earths could fit inside the sun. And you can see in this picture, there's a little tiny dot next to the sun that would be what the Earth would be if it were traveling that close. Luckily, the Earth never gets that close to the sun, so it would be burned up and quickly fall in. So the Earth is very, very, very tiny compared to the sun, and huge prominences, which are gas clouds, such as you see in this image, get lifted off the sun, and they're incredibly large structures that move very rapidly. So the radius of the sun is big, and it's a characteristic size scale for stars. So we're going to be talking about how big stars are, how small stars are, and the typical size is about 100 times the size of the Earth, which is a typical stellar size. All right, so when we look at the planets in comparison, we see that the planets are pretty small compared to the sun. Jupiter, even the king of the planets, which is 90% of all of the mass of all the planets, is in Jupiter, and it's only about 10 times smaller than the sun in terms of diameter. But Earth is about 100 times smaller in terms of diameter, and I like to include Pluto as well. Some people don't call it a planet anymore, but I do because I knew Clyde Tombaugh, the guy who discovered Pluto in 1929. He was one of my mentors at New Mexico State. He was a great guy. So I would like to move Pluto up to the planetary thing, and I even found these really cool children's wooden blocks the other day at a little knick-knack store that had Pluto as a planet. So go Pluto! Anyway, so there's the sizes of the planets with respect to the sun. This is not their distance, though. You can't do both at the same time. It's just not possible. You can do the sizes, but you can't do sizes and distances and do it relevantly on a computer. Well, at least on a computer screen. You got to get outside to do that. All right, what's the mass of the sun? Now we're going to start talking extraordinarily large numbers. So the mass of the sun, or M sub sun, is about 2 times 10 to the 30th kilograms. And so for those that are math disinclined, that x is a times. The 10 to the 30th is a 1 with 30 zeros after it. So it's a 2 times 10 to the 30th, or basically a number 2 with 30 zeros after it. That's enormous. Now, the mass of this Earth is about 6 times 10 to the 24th kilograms. So, if you wanted to put them on a balance, it would take about a third of a million Earths to balance the mass of the Sun. So the Sun is more massive than anything else in the entire solar system, including the Earth. All right. So the next thing is that we're looking at the average density. The average density is you take the mass of the Sun and divide it by its volume, and the average mass of the Sun works out to be, compared to its volume, is about 1,400 kilograms per cubic meter. That's how we read that. So rho sub Sun, or density sub Sun, is about 1.4 kilograms per cubic meter. Water is about 1,000 kilograms per cubic meter, and the Earth's average density is about 5,500 kilograms per cubic meter. So the Earth's average density is much more dense than the Sun. So therefore, but the Sun's much more massive. So there must be something a little bit weird, maybe down in the core, something's happening. But the average density. It's not the same density at the core, and it's not the same density at the surface. The Sun's density varies wildly. Whereas the Earth's average density, by comparison, doesn't vary as much as the Sun's does. All right. Next thing we talk about is the composition of the Sun. What is the Sun made out of? Well, it's meant 70% of it by mass is hydrogen, which is just a proton. We can ignore for now the electrons, because the electrons are very, very tiny compared to the protons. And by mass, the helium nuclei make up about 28% of the Sun, and about 2% are heavier elements, heavier than hydrogen and helium. So oxygen, nitrogen, carbon, neon, boron, uranium, iron, everything you can think of, everything else in the entire periodic table, that makes up only about 2% of the mass by mass of the Sun. And that's why the average density is so low, because hydrogen is a single proton. The average density, most of what Earth is made out of silicon and oxygen, make up silicon dioxide, or things rocks. So rocky materials such as carbon, oxygen, nitrogen, iron, the heavier elements. The Earth doesn't have as much hydrogen or helium as the Sun by comparison, so therefore the Earth has less. And that's the surface composition of the Sun. The composition changes as you go deeper into the Sun, but in general, if you were to average it all out by mass, the total mass at the surface is 70% hydrogen, 28% helium. All right, so that tells us something very interesting. And how do we know that the Sun's composition is this? That's really critical. So, because has anybody been to the Sun? No. Nobody's ever been to the Sun. Nobody's ever scooped up anything from the Sun. So how do we do it? We do it with spectroscopy, which we talked about before, and we will talk about soon. All right, so the average composition in terms of numbers of atoms, so we can then say, instead of just by mass, we can say the numbers of atoms, which is a different sort of concept of the density of it. But we see that by atoms, hydrogen makes up almost 90%, or roughly 90% of the number of atoms of the Sun, which means it's 90%, 91% just protons zooming around, and about 9% helium nuclei just running around, which in a typical helium nucleus has 2 protons and 2 neutrons. And everything else is so much less by the total number of atoms. The entire Sun is almost completely made up of just hydrogen. And hydrogen is not so massive, so therefore the mass is lower. And helium is more massive. There's four objects in the core rather than just one, in the nucleus rather than one. So therefore, helium being only 8% of the total, 9% of the total, you multiply that by 4, and you get really close to the total mass of that. But why isn't it 4 times 9, which would be 36? And that's because a significant fraction of the helium is in the form of tritium, which is, not tritium, which is light helium, light helium, which is helium-3, which only has 1 neutron, not 2. So, but of all the rest, oxygen, carbon, nitrogen, silicon, magnesium, neon, sulfur, and those are the big ones. And notice what it's made out of. Oxygen and carbon are critical for life. Pretty much everything in there is critical for life except for neon. So it's interesting. These are really, really interesting things that the Sun is made out of. All right. So, okay, how does the Sun rotate? There's another bulk thing. Well, we can measure the speed with which sunspots go around the Sun, and we find that at the high latitudes, it's moving a lot slower than at the equator. So it actually rotates a lot faster at the equator than it does at the poles. So it's interesting. And inside, it rotates a different rate altogether. And that can be measured by what's called astereoseismology or helioseismology. Looking at well, that's interesting. Also, that last one of the 27 days inside is also strongly model dependent, meaning what is happening in the core of the sun and how do things change as they come out. But it also can be indirectly measured by looking at the vibrations or ringings or waves on the surface of the sun. Well, the real trick is that what we find is that simply because we see that happening, the sun is not a solid. There is no solid surface to the sun. As the sun rotates, it twists itself up. It's a big ball of gas. There's no place to land on. There's no hard surface. It is gas all the way down to the center. All right. Next, we look at the magnetic field of the sun. It's 10,000 times more powerful than the Earth's magnetic sun. And all of the features that you see on the surface of it, these bright spots, these hot spots, the prominences, flares, everything, all of the surface features are driven by the strong magnetic field of the sun. And that strong magnetic field is what it does is that if a charged particle, such as a proton without any nucleus, with an ionized proton, is on the magnetic field, it will follow the magnetic field line, so will electrons. And so what you see in that upper right-hand corner of the prominence is ionized gas that's being lifted off of the surface as the magnetic field changes. And the magnetic field changes a lot. It's it's flexible and fluid as a thing, and it originates, and it's the source of what we call space weather. And space weather is the thing that affects satellites around Earth and can cause power outages here on the ground. All right, what's the surface temperature of the sun? It's almost 6,000 Kelvin. T sub sun is about 5,800 Kelvin, and that's hotter than anything you find. Some things that you'll find that are that hot would be maybe special bulbs of light that you might see in a theater. So you go to a Broadway show, the tiny, 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 tiny bulbs might be about that hot. And but that's funny is that, well, is the sun burning? And if something's that hot, you'd expect it to be burning. But the answer is no, the sun's not burning, because what is burning? Burning is the rapid combining of oxygen with something made of carbon and to produce carbon dioxide. And it is the rapid change of chemical structure inside of something such that gases are released. But it's a fast oxygenating process. That's what burning is. And you only get burning when there's oxygen. Well, there's not a lot of oxygen on the surface of the sun, as we've learned. So why does the hydrogen glow? Why does the helium glow? It glows because it's really hot. And anything, doesn't matter what it is, it can be a solid, it can be a liquid, and it's a gas in this case. A gas can be so hot and so dense that it just simply glows. Now that's fascinating. So it is more like the glow of molten iron, but the sun's not molten. It's a gas. So molten's still like a solid that kind of moves. It's a fluidic solid. That's molten iron, or flowing iron, which is a liquid state of iron. But when we think about this, it's like the sun's not a liquid. It's a gas. It's not a solid. So it's in a state of gaseousness, and there's no crystalline structure to make up the sun of any kind. So it's just a hot, glowing gas that's not burning. All right. Then we say, well, if it's hot, what is the energy output? And the energy output is what we call luminosity. Luminosity of the sun, L sub sun, is a standard that we'll see all throughout an entire astronomy course. It's about 4 times 10 to the 26th watts, and that's the same as 10 billion 1 megaton nuclear weapons exploding every second. Now, how many 1 megaton nuclear weapons do we have on the surface of the Earth? At the height of the Cold War, it was on the order of a few thousand. So, or 10,000 or so. Basically, there's more happening in the center of the sun than all the nuclear, maybe 500,000 times the total number of nuclear. Yeah, it's like, okay, 500,000 is about 500,000. And you take about roughly 10,000 or so nuclear bombs that might have been, or about 1 megaton or half megaton or kiloton nuclear weapons. Multiply out the total constructed number of nuclear weapons that have ever been constructed by the entire human race in its entire existence since we started building them in the 1940s and detonating them. You'd have to have 100,000 of those things, those events, those sets of nuclear bombs that have ever been constructed, the most terrifying weapons, to equal what the sun does every second. Wow. And that's more than we do in this wattage, the amount of wattage that the sun puts out every second, or joules per second. That's what 1 watt is. 4 times 10 to the 26 watts. That's more energy that's being put out per second than has been put out in the entire history of all the recorded industry since the Industrial Revolution. And that's what's happening every second. It's a lot of energy output. All right, so the energy output, that's fiducial value, L sub sun, which is 4 times 10 to the 26 watts. We'll see it again and again and again inside this astronomy course. And the solar constant is what we get from the sun. So the sun goes out, all the sunlight goes out in every direction, and at 1 astronomical unit away, or 93 million miles away, or 150 million kilometers, or million meters, 150 billion meters, is 150 million kilometers is what we get. And that's equivalent to 13 normal light bulbs on a kitchen table. So take a standard desk, like you might get, and a standard work desk is about a square meter is about a meter squared. And so imagine you take 13 100-watt light bulbs and put them on your kitchen table, and then put your face right next to all those things. That's what the sun is putting onto the surface of every square meter on the surface of the Earth at the distance of 1 astronomical unit. That's what we get. That's what you get. That's what every place gets. That's 1 astronomical unit away, whether it's above the sun, below the sun, behind the sun, to the left of the sun, to the right of the sun. The Earth just intersects a tiny, tiny, tiny fraction of all of that output. And what we call that wattage per square meter at the surface of the Earth, we call that the solar constant. And the solar constant is the wattage that is received on the surface of the Earth per square meter. And it's an amazing amount of energy if you really think about it. So imagine you take, if it's 13 normal light bulbs per square table, imagine we hooked up light bulbs basically every 12 inches on the surface of the Earth, a 100-watt light bulb, and then turn them all on. That's what we would have to do in order to equal the sun's output that we receive on Earth every second. All right. Next, what kind of star is the sun? If we take the light from the sun, and pass it through a prism, and then compare it to other stars, what we find is that the sun is like what we call a G-type star, and specifically it is a G2, which means it's a little bit cooler than a G0, and it is a main sequence type star, or a G25 type star, and that's what we call that. So if we compare the sun's spectrum to other nearby stars, we find that Alpha Centauri, one of the nearest stars to us in the sky, is actually just like the sun, which is funny. It's about 3 light years, just a little bit, about 4 light years away, and it's one of the closest stars to us, and it has the same exact spectral signature as the sun, so that's kind of cool. So where does the light from the sun come from? And that is really the biggest question of all, and that's what we're going to really address in the coming lectures, is how the sun produces the light that it makes, and how long will it be able to do that? So that's a good question. And I think this picture is from a friend of mine, Stan Honda, who took this picture from, if you go to stanhonda.com, I think you'll see this picture on his website. Well, that's a bit about the sun and some basic properties, and we're going to use all these basic properties in future lectures as we figure out what's going on deep inside the sun. And we'll see you next time. Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. This time we're getting away from the basics, bulk properties of the sun, and we're going to talk about the sun's appearance. And what does it look like on its surface? So the sun, as you can see in this image, is in ultraviolet light, or extreme ultraviolet light, taken by the Solar Dynamics Observatory, which is an orbiting spacecraft, and with its arrays looking at 171 angstroms, which is approximately 10 times shorter than short visible wavelength light, or extreme ultraviolet. This is called extreme ultraviolet view of the sun. And we can see all sorts of very interesting features on the surface. We see over on the left-hand side some loopy type structures we'll call prominences. We have the prominences seen top down, which are the darker structures. We see like wisps going away from it. We call that the solar wind or the corona. And we also see hotspots, which are also active regions, which might contain sunspots, and usually do. They contain sunspots or other active things. And down close to the what we might say the surfaces, it kind of looks hairy, and those things might be called spicules. But let's see those more close up. Okay, so first things first, when you're done with this video and looking at it, you should be able to answer these questions and others. So do take a look at them and take a look and see if you can figure out them, and pause this thing and go back and look. This image of the sun was taken by Dr. Vishnu Reddy from University of Arizona. He was in Glendale, Wyoming with myself. I saw the total solar eclipse of 2017, and it was wonderful to go see. When the solar eclipse occurs, you get some amazing views of the sun. So why do we study the sun? There are numerous things, and we'll discuss these four in brief right now. We study the sun because there's a connection to our climate. Since it's the primary source of light and heat on Earth, everything that the sun does can influence how warm or hot the Earth is, and so it is the fundamental driver of all climate on Earth. When we know about what's happening on Earth, we can know about the history of the climate on Earth. If we know about the history of climate on Earth, we can understand, maybe potentially help us understand what might happen in the future on Earth. And as possibly, if we can understand short-term variations and their effect on the Earth's climate, that would be good too. All right, so first and foremost, we study the sun for that. Also, very practically, we study space weather. The sun, as you saw in that first image, emits what we call the solar wind, or particles are continually streaming off of it. Enormous amounts are continuously streaming off the sun and flowing out past into the interplanetary space. So this flow goes extraordinarily fast. It transmits it carries the sun's magnetic, or carries the print of the sun's magnetic field with it. And as it does so, it pumps the energy of the sun's magnetic field into the Earth's magnetic field, and that can influence satellite weather, communications, as well as satellites themselves. If it's an extraordinarily enough violent solar wind flow for whatever reason, then the Earth's and planes might need to be grounded, or if it's very violent geomagnetic storm, there might be power outages on Earth. So understanding the nature of space weather, or what the sun is doing to the space between and in the environment between the planets, is incredibly important. Because without understanding it, we can have big problems, as we'll see later. Third, the sun is a star. And while the first two are really important in terms of very practical aspects for life on Earth, the third one is the nature of astronomy course, because the sun's a star, and since it's the nearest star, it allows us to understand details about other stars. So it's the metric by which we judge all other stars. And understanding how stars work, it starts with the sun. And we should be able to expect that if we go, or we're able to imagine ourselves next to another star, we start first with images and thinking pattern of the sun, and then try to imagine what it might be like different over there. And in fact, the sun as a star fundamentally tells us the nature of what stars are, and stars are the building blocks for galaxies. And then if we think about then galaxies are separate things we'll talk about later. So the physics of stars are very important, and how the sun behaves as a star is important. Finally, there are some very interesting questions in physics that come out of studying the sun, and you can, instead of building multi-billion-dollar large hadron colliders and so forth, you can say, well, I've got this idea about how the nature of physics works, and what is the nature of physics, and how do particles interact on a nuclear level. You can say, well, the sun has to be doing nuclear fusion, and we'll see why in future lectures, that the sun produces the energy that we see by nuclear fusion. And as such, that nuclear fusion then gives us a test, a way to test our understanding of nuclear physics. So this is a really interesting way of talking about it. So in short, we have some important reasons to study the sun. So some other outstanding questions about the sun in terms of the future, which we might not actually get to, but we might in future times, is that how does the corona of the sun get heated? Nobody really knows. The complexity of which a solar flare arises, that's still an open question. It's mostly open, but the basics are understood. But how difficult it is to actually understand where a solar flare comes from, and we'll see what those are shortly. And sunspots come and go on the surface of the sun. That's incredibly important understanding because that links to climactic change apparently as well. And missing neutrinos is a particle physics question. Those are some principal questions. Some of these are answered better than others, but these are some incredibly important questions about the sun. Now, everything that we're going to see about surface features on the sun is related to the magnetic field of the sun. The magnetic field of the sun is many thousands of times stronger than the Earth's magnetic field. And all of the things that we see on the surface of the sun, all of the surface properties are because the sun's magnetic field is not uniform and varies wildly and varies rapidly and can vary and changes with time. Unlike the Earth's magnetic field, which appears to be stagnant at the Earth's surface, it too is changing, but not with the dynamics of the sun. So the sun's magnetic field does everything. And one of the major satellites that's observing the sun today is called Solar Dynamics Observatory, and that's a NASA-based mission, and it has a series of telescopes and an ultraviolet exploration, and it also is able to detect motions on the surface of the sun, which allows it to image the magnetic field on the surface of the sun, and it takes images of the sun in various wavelengths, one in 10 wavelengths every 10 seconds, or one of those wavelengths every second. So the Solar Dynamics Observatory is designed to see very fast changes in order to understand what the entire disk of the sun is doing. Previous missions, such as Stereo and SOHO, didn't have the cadence or potentially even the size of Solar Dynamics Observatory. And SDO's goal is mostly to understand space weather. Its goal is to hopefully predict it. And in order to do that, they outfitted it with this little satellite with an ultraviolet explorer, ways to image the atmosphere of the sun in multiple ultraviolet wavelengths, as well as looking at the Doppler effect on the surface of the sun and being able to image the magnetic field of the sun through Zeeman splitting. So we're going to get some terminology, but the surface of the sun that we see in the disk in the sky, we call that the photosphere. And the photosphere is the surface of the sun from which the visible light appears to come. And that's defined as the location in the surface of the sun. We'll call it the surface, but it's not really a surface. The photosphere is about 100 kilometers thick, and it's still a gas. So even though it appears to have a sharp edge, the sun's size is so incredibly large compared to the thickness of the photosphere that it looks like a sharp edge. But the photosphere itself has edges that go out and appear to be darker, and it's called limb darkening, where the edge of the sun, or the limb, we should call the edge, the outer ring of the disk of the sun, we call the limb, appears to be darker. And that's because when you look towards the limb, you're looking at higher and higher elevation above the deeper portions of the sun. And as you go up in elevation from the deeper portions, it gets cooler in the photosphere. So therefore, since it's cooler, it is darker. So when we look in the center of the sun, or smack in the center of the disk, it looks brighter as well as yellower. And so that is because we're looking deeper into the sun, and so we see it where it's brightest. But the photosphere itself is where we get the visible light from the sun. Right, and the image that you're seeing here shows a progression of sunspots passing across the sun. And as we know, the sun rotates. So the photosphere is not a visible surface, and since it's about 100 kilometers thick compared to the sun's 700,000 kilometer radius, yes, you can't tell that it's an edge. So that's what we call limb darkening, and this image definitely shows this. This image was an image taken of an active region, and we can see an enormous active region is seen by the SOHO satellite, or the solar, by one of NASA, another NASA mission, and that huge looping object that's in the middle. These are all sunspots, and these are active regions, especially the center one, which back in the end of October in 2003 launched an enormous solar flare. And that solar flare had some problems on here on Earth, and it caused some issues down here on Earth. So let's look at the sunspots and what they are. And sunspots are really critical things because they look like blemishes on the surface, on the photosphere of the sun. They're cooler regions on the surface of the sun, and they have these very strange and interesting shapes. And this image was taken by Alan Friedman, who's a very interesting solar observer. All right, sunspots appear darker because they're slightly cooler than their surroundings. And so slightly cooler still is very hot. It was just 4,000 Kelvin versus about 6,000 Kelvin for the brighter areas of the sun. And we can see that they appear to be, that material in the sunspots appears to be moving, but it's not like it's a hole in the sun. It's not like there's no sun in the sunspot. No, it's just simply much cooler. So in the same sense that if you look into a fire at a campsite and you see that the coals look dark compared to the fire, you know that they're pretty hot and you wouldn't want to reach in there and grab them. It's just that they're cooler than the surrounding gases of the flame, and so therefore you wouldn't want to, they look darker. Now, again, the sun is not on fire. It is just so hot that it glows. And the reason the regions are darker is simply because they are cooler. And the central region is what we call the umbra. And the umbral region is a place of extraordinary magnetic field strength. And it can be, the sunspots themselves are where can be incredibly strong compared to the surrounding the sun and compared to the Earth's global magnetic field. Sunspots themselves can last for a few days. Their appearance changes very frequently. They are dynamic objects. They change with time, and they can grow in size and then shrink in size. They can live for a few days or up to many weeks. And the outer portion we'll call the penumbra, and they always come in pairs. So sunspots come in two sets, where one set is magnetic north and the other set is magnetic south. So they come in pairs where one is in North Pole and one of us is South Pole. So we can imagine that underneath the photosphere, if you wish to imagine this, that there's some sort of magnetic, like, even think of those old bar magnets or those horseshoe magnets where one end is north and one end is south. And the magnetic field is poking out. And that's not a bad example because something like that is happening in the sun. Of course, there's no big old bar magnets inside the sun. It must be because of the flow of electrical charges deep inside the sun, where the magnetic field then is generated by this current flow, and that current flow then pops up through the surface. All right, also sunspots are enormously large. Most of them are larger than the Earth, and some of them can be even larger than Jupiter. So sunspots can be catastrophically large in size, and to see that they move and change and alter their appearance rapidly is really very interesting. All right, so this was another set of sunspots taken by Alan Friedman back in 2011, and we can see that some of these sunspots are really big. Remember that the Earth there's approximately 100 Earth diameters across the sun. So each of the sunspots that we're looking at, that were taken by Mr. Friedman, these sunspots are much larger than the entire Earth. These are huge sunspots. Okay, so you saw on the background, there is kind of a structure, a honeycomb sort of structure, and they have a special name. Those are called granules. And granules are the visible top layer of the convection zone of the sun. So we can think of the sun as continuously burbling and boiling, if you wish, but it still is gases. So those are hot gases that are rising, and when they're very hot, they glow. And when they emit their light, and they get to a place where they can cool off enough such that they emit light, that's when we see the light coming from the granule. But because it's a hot gas, if it emits light, then it cools off. If it cools off, then it'll sink because a convective flow, you have hot gas rising and cool gas sinking. So each one of those little nodules is actually the center of an upwelling flow, and the dark places between them are where the hot gas has cooled off and now it's sinking back down. And the reason it's redder as opposed to yellow is because it's cooler. And so it has emitted its light, it's emitted its heat to space above it in the solar atmosphere above it, and then it is now cooling off and sinking. So these things can be very, very, very large. These granules can be up to the size of a continent. They can be about 1,000 kilometers across. And so they move around and provide the base of the photosphere. And basically the granulation that we see here, those are the things that basically are what we call the photosphere. So the granulation of the photosphere is it. So granules are therefore pretty small features, and pretty small is 1,000 kilometers, or about 600 miles across. And they cover the entire surface of the sun except where sunspots exhibit. But remember something, each individual granule lives for only about 20 minutes or so. So you have this structure on the sun that's hundreds of miles across, 600 to 1,200 or 1,000 miles across, about 1,000 kilometers across, that rises up, emits its light, cools off, and then descends back to the sun. So this is an enormous, enormous roiling, windy place because it's all gaseous. So you can think of these as upward welling winds, and that's a really good way of thinking about it. So the flow in the granules can be extraordinarily fast, and many miles per second, about 15,000 miles an hour. And they actually, because of that, will produce sonic booms at the surface. So there would be interesting waves that get produced because of how fast they move. And so they themselves will create waves of basically pressure waves, and those would be sonic booms. So these things are moving faster than the speed of sound, which is really interesting. Something about the size of a continent, a gaseous cloud, moving almost that's about the size of North America or larger, moves up or down at faster than the speed of sound. Really interesting. Okay, but then you can actually look at much larger structures, and these granules can be grouped into what are called supergranules, and they can be much larger than the Earth, and about 35,000 kilometers across, which is bigger than the Earth by a factor of, say, 4 or so. So 4 or 5 times the size of the Earth, and we see these large, large, large structures, and they're called supergranules. And so we can think of them as a basic, huge bubble upon which the minor granules flow. So there's bubbles on top of bubbles on top of bubbles, or more specifically, bubbles of bubbles. And so a supergranule is a bubble of bubbles. They tend to be much slower moving, but they also are gradually evolving too. So it's kind of a scale sort of issue, and we notice them by looking at a Dopplergram. And so this particular sub-image is a Dopplergram that shows the speed, basically the emitted light at one wavelength. And if it's brighter, it's moving towards us. If it's darker, it's moving away from us. And so you get a Dopplerogram of these large objects. And since this is the entire disk of the sun, we're seeing very, very, very large features that are bigger than the Earth. And so these large wave-like structures have granules inside of them, and then they move up, emit all their light, and then flow back down as a unit. So that's the granulation and sunspots of the photosphere, but they deposit their energy to another layer that's just above the photosphere that we call the chromosphere. And the chromosphere is cooler, as a cooler atmosphere above the solar photosphere. And the chromosphere can only be seen when there is a total solar eclipse, or you have some sort of spacecraft that it can block the light of the sun very accurately, and so that you can actually visualize the chromosphere. But the chromosphere extends above the photosphere. It is cooler, but still extraordinarily hot. And since it's hot, it will glow with this characteristic pink glow. And that characteristic pink glow is that of hydrogen. And that's what you're seeing in this image that Dr. Reddy did of the total solar eclipse back in August of 2017. You can't even see it unless the moon covers it during an eclipse. But you can see other things there too. We're not talking about the white sort of puffiness that's going around about it. That's part of the corona of the sun. I'm more specifically talking about that pink glow right at the rim of the moon, and not the pink glow that's off to the right-hand side. That's a prominence. I'm talking about that lightish pinkish glow that's all around it. That's the chromosphere, and it's chromos because it's a color sphere, and the color is pink. And the chromosphere is heated in these spiky storms called spicules, and we see them. These observations are observed by NASA's Solar Dynamics Observatory, the SDO, and we can see them near the North Pole. And so SDO gets a full view, and it's looking at ultraviolet, so we can see where the spicules are, and the spicules form. At high definition or high resolution, we can see that the chromosphere is primarily these spicules plus a dim glow right above. So the spicules are kind of like these upward shooting jets, and they change radically and over extraordinarily short periods of time. So we can think of them as almost vertically pointing tornadoes of hot gas, which is a good way of thinking about it. And those are spicules in the chromosphere. The next surface feature that we see are called prominences. And they're called prominences because, well, they're prominent. And they tend to be looping structures that lift above the sun and carry tens of billions of tons of massive material with them. So this is an example of the sun, I believe, that was taken by NASA. And this is amazing, amazing loop prominence that's extraordinarily large. Underneath that loop, hundreds of Earths could fit. It's a huge, huge, huge loop. All right, here's another example of an interesting prominence that was taken by the Stereo spacecraft, or I believe the Stereo or SOHO spacecraft, another NASA image. And it's basically a lifting gaseous bubble and loop that's coming off of the surface of the sun, and they're called prominences. And now we're going to look at it. I'm going to go and show you a couple of interesting prominences to show you how they move. And this series I'm going to show you in just a second. These prominences can be extraordinarily large, and they're guided by the magnetic field of the sun. So charged particles get in the magnetic field of the sun, they're lifted off the magnetic field of the sun, and they move as the magnetic field moves in the sun, and it's very dynamic and fluid. And as it does so, the charged particles flow on the magnetic field, and you get these kind of filamentary appearances to them as the charged particles fly along them at an extraordinarily fast pace. And I put the Earth in there just to help you see the approximate size scale of some of these things. Now we can see a video of that same loop that was taken in March 30 of 2010. And that was very short after the Solar Dynamics Observatory actually opened its mirror. And what we're looking at here is the change of the prominence over the course of a few hours. The Solar Dynamics Observatory takes pictures every 10 seconds of a particular wavelength, and so we can see how the prominence itself moves over time. And you can see the action of the spicules in the background. So don't just look at the prominence that's occurring there. We see that the spicules in the side areas are actually little shooting jets type of spikiness, and that's just by the words in the image, and also at the limb of the sun. And when I say limb, I again mean what you call the edge. So look again as it zooms out, we see a series of spiky features, and those are called spicules, and the glow right above it, that would be the chromosphere, and the prominences are above that. Prominences tend to happen around sunspots, so there's a link between these active regions, which are the glowing region that you see there, and this is of course taken in extreme ultraviolet light. But if we were to look in that area in visible light, maybe say just normal light that we would see with our eyes, we would see a dark sunspot. So there's a difference in the view that we have of the sun when we look in ultraviolet as opposed to visible light. Next thing we're going to look at is what's called the solar corona, and this was by Stan Honda. Stan Honda also went out to see the total solar eclipse, and he made sure that he got some beautiful, beautiful, beautiful images of the eclipse. And the corona is the gaseous material that comes off of the sun and streams out into space. So strictly speaking, the sun doesn't really have a solid surface, because where does it end? It really doesn't end. The solar corona is an extension of the sun. The photosphere is where most of the light that we see comes from, but the corona is only visible when the photosphere and chromosphere are both blocked. So you need a total solar eclipse in order to see it. And if you go to see a total solar eclipse, yes, you actually do see this in the sky. It's absolutely fantastic and gorgeous. But the corona itself is also rapidly changing and guided by the magnetic field and is a product of the magnetic field of the sun. In fact, if we look at this thing on the right, we see that it has this kind of leaf sort of structure on the one that's pointing at 2 o'clock. We see it's kind of broad in the side and then it kind of pinches at the top. And that's kind of very common for appearances with the corona. Well, if we actually take a spectral analysis of the chromosphere and the photosphere, we can determine the materials that make up the sun's atmosphere. And this is a sample sort of thing that we might see. But if we were to actually go to the McNath Solar Observatory, which is down in Tucson, Arizona by the border, at Kitt Peak, we find that a high-resolution solar spectrum shows enormous numbers of spectral features. And simply by looking at all of these spectral features and taking out what we call telluric lines, which are absorption features due to the Earth's atmosphere, we can determine we can observe in the solar abundances and what exactly makes up the sun. And when we do that, we actually discovered that the sun's atmosphere is about 90% by atomic number, about 90% hydrogen, and by number about 9% helium, with very trace elements of everything else. So the action of all of those things is mostly because the sun's mostly hydrogen and helium, and all of the other lines that you see come from extraordinarily trace amounts of the rest of the elements. So the solar atmosphere itself, if we look at the entire thing, it starts at the photosphere at about 6,000 Kelvin. The chromosphere is when it gets cooler. It transitions then into the corona, which then is another 10,000 kilometers up, or about 2 Earth diameters up, or about 2 Earth radii up. And then we get out into space and it heats up enormously. It gets up to millions of Kelvin. So the corona itself is extraordinarily hot gas. It's very tenuous and visible in X-rays because of the temperature. But it's interesting that it actually has this temperature profile, and the study of this and why it cools down for the chromosphere and why the corona then gets so much hotter. That's an area of active research. So occasionally we don't see these things. And this is a view of the quiet sun when there's no sunspot activity and no prominences and everything like that. And that's all interesting and everything. And this is where looking at the sun in visible light. So we see invisible light at a specific wavelength of 6562.8 angstroms, which is in the red region of the sun. We see that the sun has that mottled appearance of the granulation, and we see a couple of tiny sunspots and very few spicules and very modest prominences. But this is what we would call a sun that has very quiet appearance to it. And sometimes we have magnetic fields and sunspots. So let's look at that in more detail. So how does the magnetic field of the sun create a sunspot? Well, the magnetic field is generated deep inside the sun, and occasionally the magnetic field bursts through the surface, and when it does so, it's doing to try to release energy. And so the magnetic field becomes tangled inside the sun as there's rivers of current, literally current rivers of electrons flowing very quickly in a literal current inside the sun, and that creates a magnetic field as a dynamo effect because of the differential rotation of the sun. So the magnetic fields get set up, and occasionally the magnetic fields bunch up inside of the sun and therefore poke through the surface. And when they do, the magnetic field lines, they have a direction to them, and the north end of the magnetic field and the south end of the magnetic field, where they puncture or at least go through the photosphere, that's where sunspots occur. So where the magnetic fields come through or breach the photosphere, they cool off the surrounding photosphere by giving a way for the particles to remove their energy. So they can flow along the magnetic field lines, and as they do so, they can emit energy and therefore cool off. Therefore, the sunspots are places where it's cooler. And so that's why you also get them in pairs. Why you have sunspot pairs is because they trace the magnetic field of the sun. So the magnetic field traps the gas and that allows the sunspots to be cooler and deep inside the convection cells. Because remember, there's this roiling convection that's happening under the sun. And so we have all this motion of hot, hot, hot gas, which is essentially what we call a plasma. And a plasma is an ionized gas. And so if you have motion of an ionized gas, you're going to create electric fields, and electric fields in motion create magnetic fields. And so it's an incredibly complex interplay, which creates magnetic fields that then burst through, and that's the only way that they can go is that the magnetic field itself creates a loop. And then that magnetic field is invisible unless it has hot gases in it. And then those hot gases then can emit light in order to cool off as they move through the magnetic field. And that's what we're seeing here is that as the hot gases move through the magnetic field, they cool off. And as they cool off, they emit light, and that traces the magnetic field. And so they aren't solid objects, and they're not things. Those are just filaments or rivers of hot gas that are charged particles that are flowing through these magnetic fields. All right, so now what's interesting is as the sun rotates differentially, there are times when the sun has a very even magnetic field, and then over time, the magnetic field is tied to the gas inside it, but the sun rotates differentially and so drags the magnetic field around and really tangles the magnetic field up. So occasionally you have magnetic field lines that then get parallel to each other, and as they do so, there's a pressure that happens between one magnetic field next to another, and in order to relieve that pressure, they poke through the surface to create those sunspot pairs. And that's what we're seeing here, a nice quiet sun where the magnetic field is all nice and regular. And then as the uneven rotation rate of the sun, slower at the poles and faster at the equator, tangles the magnetic field, eventually gets so tangled and all the magnetic fields get so close together that it's much easier to release that energy by bursting up and getting out of each other's way. In just the same way when you have like toy little magnets, they really kind of jump away from each other when you push them together and want to go to a more even state or a more lined up state. And so this is the attempt of the gases in the magnetic field to kind of make a more lined up state. But there's incredible energy associated with it, and they can't do it, so the first thing they do is create a sunspot. So that means that solar activity changes with time, and you can go from quiet times to active times, back to quiet times, back to active times. So we have the solar activity changes with time, and how many sunspots there are changes. And if we look, we'll find that we can actually hunt for this throughout history. When Galileo first started looking through a telescope, one of the things he did was to stare at the sun. And you shouldn't do that, but he was drawing things and he didn't know. But it was very, very bright. But he did his own drawings of the sun and saw sunspots. And if you make an image, make a little movie out of the sunspots that he saw, then you actually see that there's 36 plus drawings, the 36 drawings that he did, shows that these sunspots move across the surface. Well, we don't see those sunspots today, we see different ones. And in fact, the sunspots that he drew changed from day to day. The sun has a cycle that every 11 years, the sunspots begin at higher latitudes and then get more and more and more concentrated. There's more of them, and they go to lower and lower latitudes, closer and closer to the equator. So as a sunspot cycle occurs, you start from very few sunspots, then a few appear way at high latitudes, then more appear at lower latitudes, and they get closer and closer to the equator, and there's more and more and more of them, and then all of a sudden they all dissipate. And then you start again. So you can count, the solar cycle is a counting of sunspots, and this has been done for a very, very long time. And this is what I mean by that counting set. We can determine how you want us to count them. It's like how big they are, how small they are, where you see them, and so forth. But if we see as time progresses, that this 11-year cycle shows that sunspots there's for a very short period of time, we have a solar minimum, which is the minimum number of sunspots. Then you have a solar maximum, where there's a maximum number of sunspots. And then all of a sudden they go to the equator and then dissipate rapidly, and we get a minimum again. So this is the solar cycle. And in fact, it's actually a 22-year cycle because we switch magnetic polarities. It goes from magnetic north to magnetic south and so on. And therefore, the number of sunspots is every 11 years, but if you add in the magnetic polarity, it's every 22 years. And then there was an interesting time right after Galileo started looking called the Maunder minimum, where there were few, if any, sunspots. And it was not for want of looking, because people really were looking for them at that time. We'll get back to that in just a second. The solar cycle has been observed for an extraordinarily long time. We can see from here, from David Hathaway's work at NASA, that the sunspots are summarizing all the total number of sunspots throughout history. And he started his work looking at the historical place from 1750 and onward. And we can see there's been a number of sunspot cycles. And these are good counts of people looking at the sunspots for a long period of time. And if we then go back all the way to using Galileo's data and start from 1612, we see that sunspot counts have been fairly consistent, that this cycle has been consistent roughly since the year 1750. But there was a time, roughly around 1650 to roughly 1700, that's called the Maunder minimum, where there were no sunspots. People were counting and were looking for them, but saw none. And it actually corresponded to a time of cooling on the northern hemisphere. It's interesting that that would occur, but nobody really understands the nature of why that would occur and what the point of that is, or if there's any meaning to it. But understanding what the Maunder minimum is and how it actually influenced our climate on Earth for those 50 years, it's a fascinating study. So decadal long cycles in the sun actually do have influence on the sun, on the Earth. And so the solar cycle affects us here. Next to the last is some very interesting stuff. There's solar flares. Sometimes on the surface of the sun, on the photosphere, you get extraordinarily violent events where active regions, like this massive sunspot region that's smack in the middle of the disk of the sun, there's some really, really, really huge, massive active regions. Now we call them active regions because there's going to be flares, there's going to be prominences, there's sunspots, they're called active regions. And solar flares can be graded from various types, but one of the largest types are called X-class solar flares. And though if it's a logarithmic scale, and so if you have an X-type 10 or an X-type 17, it's an extraordinarily large output. And so what happens in a solar flare is the following. We can see that in this particular thing, that was the image from then, and these are the satellite images that were taken by the SOHO spacecraft in 2003. The green image in the upper left shows the visible light image, or at least an ultraviolet light image of the sun. It's an ultraviolet light image that shows the solar flare occurring, and the solar flare is a momentary brightness, or some brightness that occurs over the course of a few minutes. And it's enormously large areas. The total energy output that can occur in a solar flare, you can see up in the green, which is in the ultraviolet, it will be on the order of tens of billions of nuclear bombs, 100 megaton nuclear bombs, all at once over the size of an area much larger than the Earth. So you can think of it as one of the incredible large output of energy. And because of that, you get X-ray emission and you get gamma ray emission, and there's the temperature on those areas in the sun can reach 10 to 20 million Kelvin, which is actually hotter than the center of the sun, and you get nuclear reactions on the surface of the sun. So that's what's happening with the solar flare event that you're seeing in the green. Then the result of that is which is shown in the red and blue, which you see after the solar flare occurs. We see the corona in the background, which is kind of this constant sort of flaring out on the sides. But then you get this burst that occurs. When the flare happened, it emitted an enormous amount of material, and might be hundreds of billions of tons of mass that flowed out at nearly the speed of light out from the sun. And it gets to Earth in a couple of days later. And when it gets to the Earth a couple of days later, you get events, or even hours later, depending on how fast it's going, which can actually cause the sparkling that you see in the in the telescopes of the SOHO spacecraft. So we see a continual outflow, which is called the solar wind. We see the corona, which is the constant streamers that are coming out. And then we see the coronal mass ejection that was directed straight at Earth on that date. That caused a power outage in 2003. And now I'm going to use a NASA video, which is a really interesting video that shows a prominence and an eruption of a coronal mass ejection back in 2013. And we see the prominence that occurred on the limb of the sun, and there's the prominence occurring. You can see the spicules and the granulation on the surface of the sun, and we see the flaring contrast. But as the sun is emitting this material, it also had a flare. So the Solar Dynamics Observatory could only see the prominence and the flare occurring, but the rest of the imaging was taken by, of course, the SOHO spacecraft as well as the STEREO spacecraft, which are also orbiting the sun. So the Solar Dynamics Observatory takes a small amount, and there you can see the link between the prominence and the SOHO spacecraft's observation of the coronal mass ejection that came off of the sun after the prominence occurred. So it released materials deep into space on May of 2013, and now the SOHO spacecraft has a much broader field of view, and we can see the coronal mass ejection going out into space. And that's hundreds of billions of tons of material. The other STEREO spacecraft, which is away from, it's trailing the Earth in an orbit, so it gets a different vantage point, about a quarter of the way around the sun. And we can see the coronal mass ejection from a different vantage point as it trails the Earth about a quarter of the way around. And we're looking at the extreme ultraviolet. And now we go to the green view, which is another view by STEREO. And this is what's called, the COR stands for coronagraph, so it's covering the surface of the sun. And now we can see the coronal mass ejection from another coronagraph. So the coronal mass ejections can influence the Earth massively, and they come from these active regions of the sun. Oh, and if you want to go see these things, go look up the Goddard Space Flight Center at NASA. Their visualization stuff is fantastic. So we see a link between prominences and coronal mass ejections. So what can we have as a problem of this? The largest solar flare known to have ever happened in September 1st of 1859. And when the coronal mass ejection reached Earth, it actually wiped out the Earth's magnetic field. It was the largest possible a solar flare that's been known to have ever occurred in the history of observing the sun. After this solar flare occurred that Richard Carrington saw on September 1st of 1859, the next day, the aurora was visible all across the Earth down to the equator. And normally it's only in high latitudes, way, 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 way north. But basically it erased the sun's magnetic field, and the telegraph had recently been invented, and people could actually broadcast telegraph messages across the United States without the batteries, because the batteries themselves were blowing up. So they couldn't actually use telegraphs with the batteries. They didn't need to. The ground was charged, and so there was an enormous charge across transatlantic cabling. If a Carrington-class solar flare occurred today, we would have massive problems here on Earth, unless, of course, we chose to do a huge power outage across the entire United States in order to preserve our electronic infrastructure. And you should really know that everybody who does any kind of work inside the electrical industry knows what a Carrington-class solar flare is, and they watch spaceweather.com in order to understand this stuff. And the solar wind is therefore the particles that come off of the sun. Usually it's huge amounts of material, but for a very, very, very short period of time, a coronal mass ejection can have an enormous influence on the surface of the sun. But we can see from this graphic that actually what's happening is which is from NASA, is that the particles are being redirected. And why are they being redirected in general? Because the Earth has a magnetic field. And so here is a schematic of kind of the interaction of an active sun creating a solar flare that has a prominence that's visible to it. That prominence, that activity creates a coronal mass ejection that then travels out into space, and if it happens to interact with the Earth, some of those particles go down into the Earth's magnetosphere, which is the blue area that we see in the upper right, and can give us aurorae and amazing geomagnetic storms. So the Earth's magnetic field protects us. It protects us from the solar wind, and it protects us. But the coronal mass ejections can actually plow through and wipe out the Earth's magnetic field for a brief period of time, allowing the particles to reach the Earth and form the aurorae that it can happen in like a Carrington-class solar flare. So without the Earth's magnetic field, we wouldn't be here. We wouldn't have modern technology. We have grown up in a time where modern technology is protected by the Earth's magnetic field. And so spacecraft that live outside the Earth's magnetic field have to deal with that. And some spacecraft have been destroyed. Not all. Thousands of spacecraft are up there, but only a handful have ever been truly wiped out by it. But if there's going to be a Carrington-class solar flare, every plane's going to be grounded. We'll probably have massive brownouts or power outages just so that the equipment doesn't get damaged, if that ever occurs. And so what's really beautiful is that the source of the aurorae, and this is a view from the International Space Station, as the solar wind passes through the Earth's magnetic field, it spirals along our magnetic field, just like the particles spiral through the magnetic field of the sun. They can spiral through the Earth's magnetic field, and as they bounce around the Earth's magnetic field, as they hit the Earth's upper atmosphere, they cause the glow in the sky that's called the aurorae. And it's a beautiful thing to see from the ground, but it's really fascinating to see from the International Space Station like this. And here's what solar flares can do. They can damage spacecraft. They can cause the Earth's atmosphere to heat up and expand and therefore actually cause drag on satellites and cause them to come down. It actually can harm satellites. We saw in the solar flare that there was all those sparkles. Those are protons that are coming at nearly the speed of light and can damage the electronics of a spacecraft. And it can also create currents in the ionosphere, which basically can disrupt GPS signals. It can disrupt radio transmissions. It can also influence aircraft satellites as well. There's all sorts of crazy things that can happen. If there's cables underneath the ocean, you can have incredible ground effects from there. You can have currents in pipelines. So yeah, the sun can do things to pipelines underneath the ocean. It's amazing. So knowing space weather is kind of critical to modern society. So that's why it's done. That's why NASA has this fleet of spacecraft to understand the sun. So the solar wind mostly escapes through the coronal holes where you have where the magnetic field, where you see the loops and flares of the corona, but you see these streamers coming out. Those are the coronal holes where it's cooling from there and material is flying away. And the coronal holes can be seen because they're darker in X-rays, as the sun looks bright in X-rays, and the coronal holes are where the solar wind arises. And as the field lines loop back to the Earth, they're trapped. But if the field lines extend out into the outer solar system and out in interplanetary space, then you get those beautiful, beautiful coronal features. And then that's the origin of the solar wind. And the particles can go out, meaning mostly protons and electrons, accelerated to extraordinarily high speeds and can reach the Earth in a couple of days from 93 million miles away. So that's pretty much it about the surface appearance of the sun. So I invite you to take a look at some of these questions about the sun's appearance. Go take a look at it, and we'll see you soon. Hello everyone, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Last time we were talking about the surface features of the sun. Now let's get down to the center of things, down into the core of the sun. So what's way down in the core of the sun? What are the conditions like in there? And we see from this diagram that it can be very complicated, but below the photosphere and below the chromosphere. Deep down in the sun, the conditions are really rather strange. So let's go see what's happening down there. So the sun's interior, which we call the interior structure of the sun, is divided up into a series of areas. The photosphere is very thin with respect to the sun's thickness. But then there's directly below the photosphere is what we call the convection zone, and it's an extraordinarily deep thing, 200,000 kilometers deep or so. Below that, we have an area called the radiation zone. It has nothing to do with radioactivity. No, it is just where energy is transported via radiation. And that's about 300,000 kilometers. And the core itself has a diameter of about radius of about 200,000 kilometers. And the sun itself is divided up in these sections. The convection zone is where energy is transported primarily through bubbles of gas that are hotter and then rise through, and radiation is where energy is transported this way. So let's actually look at the interior of the sun and what is down way deep in the core. In order to understand the depth and what it is way down in the core, we have to rely on a lot of physics. And so here we go, the beginning of lots of physics in this entire series. The major aspects of physics that we're going to be talking about first are the law of gravity, Newton's law of gravity, F equals gmm over r squared, the principle of hydrostatic equilibrium, meaning it don't move, and the equation of state, meaning how gases behave with respect to pressure, density, volume, etc., macroscopic variables you might measure about a gas, and some source of energy, meaning, the sun's radiating light, so therefore it must have something to replace that energy in the form of light. And then that energy's got to get from wherever it is produced out to the surface such that it goes out into space as light. So we're going to deal with these in the next series of videos, this one and the next two, in order to get there. But first, let's talk about hydrostatic equilibrium, which is a fundamental concept with respect to stable things. Hydrostatic equilibrium, blah, 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 blah. Hydrostatic equilibrium simply means that the sun isn't getting bigger or smaller. It's not squishing in on one side and then getting bigger on the other. It's pretty much stable in every way we can think, or at least as another way of saying it's really not significantly sloshing around. And as such, the sun, because it's in hydrostatic equilibrium and it's a big ball of gas, it takes the shape of a sphere. And so the best way to think about it is that the gravitational pull of all the gases, which has mass, gas has mass, people tend to forget that, but the gravitational pressure due to the weight of the gas must be balanced by the pressure pushing against that gravitational pull. So something's got to provide that pressure, and that pressure is the gas pressure. So gravity pulls all the gas in, and the gas itself provides pressure outwards. And so there's a balance. And in hydrostatic equilibrium, let's explain this now. The deeper you go, the greater the pressure must be. So the greater the weight on top as you go in. So therefore, the pressure counterbalancing it must be greater. And this equation that we see, let's read it out because it kind of helps to read it. And it's in the form of a calculus-based equation where we're saying that the dP simply means a little change in the pressure. So that D means little change in, and the dr on the bottom is a little change in radius or depth. So there's a little change in pressure as it changes in radius or depth, and that corresponds to something related to Newton's law of gravity. And that's where that big G comes from, because that's the big G of Newton's law of gravity. The m is the mass of some element pushing down on top, and rho, that Greek letter rho that looks like a P, a kind of a funny shaped P, is the density of the material that has that mass of that region, and then r squared on the bottom is the distance from the center, so from the center of mass. Therefore, when it's in hydrostatic equilibrium, the balance in pressure means that it's not going to be pushing up or down, and it's not going to be sloshing up or down. It'll be all in balance, and so you can measure how the pressure changes with depth by simply knowing what the mass of a little element is in there, and its density, and where it is inside of there. That's what we really care about. That's hydrostatic equilibrium. And it means that the weight that is pushing down on top of a little element is being pushed back up by the pressure from below. So in hydrostatic equilibrium, if you kick the star just a little bit, what happens? Well, if the pressure dominates, meaning pressure outward, something below, then the star will expand. And if gravity dominates, it'll contract. So it depends on what you do. If the gravity then dominates, it'll contract a little bit and expand, and therefore, that if it contracts a little bit, it'll go until the pressure then pushes back, and then the pressure pushes back and expands, and then it might then say, ooh, well, there's not enough pressure to hold the gravity, so it'll contract a bit. So there's this oscillation that then gets balanced out in hydrostatic equilibrium. And eventually, when you think about this, as it oscillates between pressure pushing out and gravity pulling in, eventually it settles down. And when it settles down, you eventually get a setup where then the core is very, very, very hot and very dense and really compact, and surrounded by a much, much cooler, much lower density envelope around the core. And that's kind of what you get after a long period of, or relatively long period of time, where the hydrostatic equilibrium is established inside a star. So let's look at that really carefully, and we'll kind of see it one more time just for fun. And so we got the blue arrows representing gravity pulling in and the gas pressure pushing outward. And so as you go deeper, we started the whole thing, and we say as you go deeper, the pressure increases as the gravitational force increases too. So the deeper you go, the greater the pressure. So most stars, so how does the pressure vary inside of there? What is the thing that says what the pressure is? And we can go back to old high school chemistry with the ideal gas law. And the ideal gas law is what we're going to use in order to determine the relationship between the pressure, the density, and the temperature of the gas inside the star. So that is a very good approximation to exactly what's happening there, because it's pretty much every particle inside of a star is just is essentially a single particle. And so we can use the ideal gas law as for the incredible range of temperatures that are inside a star and densities that are inside a star. So if you compress a bubble of gas, the pressure goes up and the temperature goes up. And if you let it expand, the pressure goes down and the temperature goes down. And so those relationships of the ideal gas law exactly tells us how the interior effects go in the star. So the bottom two equations are equivalent. Let's look at the left-hand one. Those brackets mean the average of, or average pressure. The bracket around the row on the right-hand side means the average density. And the little m with a hat over it, or the dash over it, means the average mass of the particles of the gas. And kT is the expression of the energy of a particular particle in the gas. So K is the Boltzmann constant and T is the temperature. Now on the right-hand side version, we have the pressure again, but a pressure at a particular area, and V is the volume pressure of a packet of gas, and V is the volume of that packet of gas. And that's simply equal to the total number of particles in that gas times kT, which is basically the energy of each particle. So the pressure times the volume of a particular packet of gas depends on how many particles are in it, and their temperature is what the ideal gas law really says. So I broke it out here in a whole bunch of different ways to give you the exact definitions for each. And there's some things to play with, is to say what happens when you make something hotter. If you keep everything constant, what's got to happen? Let's say you keep the volume fixed and you make it hotter. You keep the total number of particles in the box the same, the volume's the same, you make it hotter. Well, of course, the pressure goes up. If you apply greater pressure on the outside of the box and you don't change the volume, then the temperature must go up. And if you expand the volume, what happens? And if you add more stuff, more particles, what happens? And so you can play like a mix game and say what things can happen if you do this and then you do that. And the Boltzmann constant is a thing that relates it's specific to the entropy, means more specifically the ways that you can arrange the gas particles inside of the box is really what the Boltzmann constant comes down to. And that relates to the energy per particle at a given temperature. So the ideal gas law says you got particles in a box under pressure at a temperature. How big's the box? How many particles are in the box? And it relates to either all of them. And it implies that all the particles are roughly the same in size, or they can be averaged to their size scale. And that's what the ideal gas law says, that these particles, when they hit each other, they bounce off of each other, they don't transform, they don't become other particles, they don't stick. They just kind of reflect off each other. Think of them as billiard balls bouncing around inside a box. That's a good way of thinking about the ideal gas law. So let's take the ideal gas law and apply it to this core envelope structure of a star, such as the sun. And the deeper you go into the star, the greater the pressure. And the ideal gas law says that if you put it under pressure, then it must be hotter and hotter and hotter. And so down in the core of the star, it's going to be extraordinarily hot, much hotter than the surface. And that's just what we expect. And the central temperature then, it's a really interesting question. What is the central temperature? How hot is it down there? Well, the central temperature has what we call thermal energy. And thermal energy describes, when we say thermal energy, we mean the average motion of particles inside the core. And the thermal energy has to be high enough per particle that it supports the weight of all the gas on top of it. And the only way for it to do that is for it to bounce around really fast. And by bounce around really fast, we mean move really fast. And if it's got to be moving really fast, it's got to be really hot. If we equate that thermal energy, which is 3/2 kT, to a typical of a typical proton, which is what most of the sun is made out of, down in the core, and to the gravitational energy it has by being there, which is the gm m sub proton, which is little p, and then compared to the entire mass of the sun, which is the m sub sun, divided by r sub sun. And so we're just saying the gravitational potential energy of a proton at the center of the sun, which is the right-hand side of the equation, and we set it equal to the thermal energy, the average thermal energy at the core of the sun. That's why the temperature sub C, meaning core, and then the little the O dot, which is the sun's symbol. So we're saying, what's the temperature at the core? We know the mass of the proton, we know the mass of the sun, we know the size of the sun. And so if we put all that together, we get the central core temperature as about 15 million Kelvin, which is extraordinarily hot. We then say, well, what's the pressure there? And we can justify the central pressure by saying, well, what is the pressure down there? And we can take that hydrostatic equilibrium equation and then merge it with what we call the mass continuity equation, which is the little one that I put there in the upper right. And those two things merge together and just put them together as like the total sun value. So replace the dP with the pressure C sub sun, and replace the dr with the radius of the sun, and replace the m with the mass of the sun, and the rho with the density of the sun, etc. And what we get is that approximate value that we have in this equation, which says the pressure of the center of the sun goes roughly like, and that's what those equivalent symbols mean. That's what those double twiddles or double wavy lines mean. This means the pressure at the center of the sun is approximately the gravitational constant, that's that g again, times the mass of the entire sun squared divided by the radius of the sun squared, the radius of the sun to the fourth power. And that's a rough approximation by taking these differential equations that we would use in calculus and integrate through using a computer, in fact, and just assigning them their global values. And that gives you an enormous central pressure. And it's like 10 to the 16th pascals, which is, a billion is 10 to the 9th. So it's 10 million billion pascals. And that is more than 100 million times the pressure at the bottom of the Mariana Trench. So yeah, it's pretty high pressure. By comparison, at sea level, the normal air pressure at sea level is about 100,000 pascals. So it's over 100 billion times the pressure at sea level. It's pretty high pressure, an extraordinarily high pressure in order to support the weight of the sun on top of it. So now we have the central temperature, we have the central pressure. Now we can measure the density of the center of the sun, and we can go back to the ideal gas law, plug that in, and determine the central density. And we end up with, if we plug in the central values for the pressure and density, we get for the pressure and temperature and give it a typical mass, which is a mass of a proton, we find that the density is on the order of 150,000 kilograms per cubic meter. Now, gold has a density of about 10,000 kilograms per cubic meter, roughly, and so therefore it is 10 times more dense than gold in the center of the sun. But it's still a gas, which is really crazy. We think about gold as being a solid, right? And it is at room temperature on Earth. But remember, the sun stays as a gas because, it's so incredibly hot. It stays as a gas even though the density is much greater than that of gold. And gold is one of the most dense objects that we know, which is really interesting. So the central density of the sun is extraordinarily large. And we can use these basic arguments to argue that this is what the central density must be and what the central temperature must be. And this was done well before, invention of computers and computing algorithms that would compute the central density and so forth. The core conditions are, the core is about a quarter of the entire radius of the sun. The temperature is about 15 million Kelvin, and the density or more specific calculations, is about 151,300 kilograms per cubic meter, compared to the surface, or roughly the envelope, or maybe just the photosphere, which the radius is about 700,000 kilometers, the temperature is much, much cooler at 6,000 Kelvin, and the density is about, so it drops off really rapidly from the center to the surface. And that's just by comparing using the ideal gas law, the equation for hydrostatic equilibrium, and the fact that there's no gaps in the stars, that mass continuity equation. We just put that together, and that's what we get as some really basic things. And because this is just simply hydrostatic and some basics of ideal gas law, this was actually understood very long before understanding what the actual, how this gets that hot and how it maintains that heat. So let's actually look now more detailed, and if we then go in a more detailed description of, well, how does it drop from the core to the surface? Well, we know that it can't just go like, here's the core value and here's the surface value. It has to drop off in some way. So again, we start at the core, it goes through the radiation zone, convection zone, and the photosphere, and then we can just dial down and say, okay, the center is the central line, and there's a peak at the center. And so we see that most of the high density area is right at the center. The densest portion of the sun is it's extraordinarily high density, and then it drops rather rapidly about just at the outside the core. So the core itself is where most of the high density area is, and the envelope structure is right outside these peaks when it's very, very low density. So in fact, it gets to be about the density of the surface of the sun well at about halfway out the radius of the sun. So the density that's about halfway out the sun is almost the same as at the surface of the photosphere, which is interesting. So it's extraordinarily high density at the core and drops off rapidly once it gets outside the core. Now then we can say, how does it vary with the temperature? The temperature, however, more smoothly varies. It still is strongly peaked in millions of Kelvin from the center, and it goes out to about 6,000 at the photosphere. But yet you can see that the temperature drops rather differently. So between these two things, between the steep difference in density and the smooth difference in temperature, there comes a point when you have that could actually draw out convection. So convection is when you have a strong temperature gradient, but not a very strong density gradient. And then that is ripe for conditions of convection. And that's what we saw on the surface of the sun, is enormous granulation and supergranulation, which is the convective cells. So what exactly is convection? Well, we'll get to that really soon. And what are the other things as well? How the sun transports energy in the core. It transports by light just simply bouncing from place to place, and that's the fastest way for it to get out. And then as soon as it gets up to roughly the surface, or about halfway out, the convection starts to come in, where the best way and most efficient way to transfer energy from inside to out is that bubbles get hot and bubbles rise and fall. And so that's about 2/3 the way out from the center, about 200,000 kilometers from the surface down. So that's how the energy is transported from the interior out. How do we know that this is even true? Well, we can actually look at the surface of the sun, the photosphere, and see that it's actually roiling, rising and falling. And then we can map how those roiling, rising, and fallings occur, and we see that the sun is actually kind of ringing like a gong. And that ringing is waves that start at the surface, go deep inside, reflect off the interior or higher density regions or higher temperature regions, and then reflect back to the surface. And so what this diagram is showing in letter A is that there are oscillations that occur on the surface of the sun, kind of like a spherical drum or a sphere, just kind of a ringing sphere. And the right-hand side image is saying that as the waves travel deep from the surface, deep down in, they get to a hot spot and then refract away from that hot spot. And that's very similar to what happens in a mirage in the desert. So if you have a very, very hot surface, like a road in the desert, you get this double image, and it's a refraction of light because of the change in density and change in temperature. And so waves of pressure can actually be refracted as well. And the different kinds of waves and how they are incident upon the surface gives a distinct pattern on the surface how they go down through the sun gives distinct patterns of what wavelengths are allowed, and that actually allows us to map the interior. And that process is called helioseismology. And helioseismology is the study of the surface of the sun and its motions up and down. And in this image, which is taken by the Solar Dynamics Observatory, what we're looking at is a speckly sort of funny image, and the dark dots are upwellings, and the white dots are where the things are moving down. So this is what's called a Dopplergram. Okay, so we'll see it again. I think it'll loop. There we go. Good, it loops. And the Dopplergram shows that the dots that are coming up, which are dark, are coming towards us. The dots that are white are going away from us. And in the center of this image is a sunspot. You can see that it's kind of stable. But look for a second at kind of the staticky sort of feeling of the surrounding areas. You can almost see what the granulation looks like, which is kind of the lumpy bits, because the white is going down and the black is coming up. So you got these kind of lumpy sort of objects. But then you might be able to discern sort of wave-like patterns inside of this. And in fact, with large computer algorithms, you can. So you can determine that over the large scales, you get extraordinarily big wave patterns that you can then map how they reflect off of the interior structure of the sun. And so Solar Dynamics Observatory has the capacity to see this Dopplergram across the entire surface of the sun. And the left-hand side of this image is a Dopplergram, but taken by the Solar Dynamics Observatory, and the right-hand side is the sun in visible light at the same time. And so we see that there's motion up and down with respect to the sun, and this can be mapped to the interior structure, and that allows us to determine the interior structure of the sun and say, oh yes, the model that we just showed you in those other things, how the density and temperature maps inside, can have an exterior appearance. So motions on the surface are dependent upon the interior conditions, specifically the temperature and density. And that study is called helioseismology, and it allows us to understand the center of the interior of the sun. Not all the way down to the core, but to some extent it does. But the core is measured in a slightly different way, if it can be measured, because nobody's ever been to the sun. Nobody can get to the sun. You can't get to the sun, take a scoop. All you get is light. And so therefore, we have to be able to see the surface patterns and understand them. And so seeing those wave patterns on the surface of the sun and how they actually bounce around tells us about the interior of the sun. All right, so there we have it, and we will see you next time on our next bit when we're going to talk about exactly what those convection cells are and all that kind of thing, and how energy gets transported, because, hey, the sun's cooling off, and at some point, it's got to replace that energy. We'll see you soon.
Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the sun, and the sun specifically, how energy is transported inside the sun. It's really important for getting to understand how the energy that's generated deep inside the sun makes it to the surface to let us see the amazing things that we do, such as prominences, solar flares, and even just that nice day on the beach. All right, so why do sunspots appear on the surface of the sun? Why are there solar flares? Where does the light of the sun come from? All of these are due to processes deep inside the sun. So today, we're going to take that deep dive into the physics of the sun and the stars. First, we know that there are significant differences between the core and the surface temperatures, densities, and pressures. Looking at all these surface variables, rho is the density, temperature is the T, m is the mass, r is the radius, and L is the luminosity. And we see that each of these has a little circle dot subscript, and that always indicates the sun. And when we look at these these aggregate things, we see that the mass of the sun is about 2 times 10 to the 30th kilograms. The radius is just under 700,000 kilometers. The density is approximately 1,400 kilograms per cubic meter. The surface temperature is approximately 5,800 Kelvin. And the luminosity is about 4 times 10 to the 26th watts. Now, when you deal with stars, these are we're rather than saying like 2 times 10 to the 30th kilograms, we're now going to define a new, more convenient unit, the solar mass. And each of these can be used as a base unit. Such as example, m sub sun, which is that thing, we'll just call it one solar mass. And one solar mass is 1.989 times 10 to the 30th kilograms. And L sub sun is one solar luminosity, rather than saying 3.828 times 10 to the 26 watts. Solar masses and solar luminosities are the ones we typically use in observations of other stars and nebulae and galaxies, and a typical massive star might be 10 solar masses, and a typical galaxy might be 100 billion solar masses. The Milky Way is about 10 to the 12 solar masses and about 10 to the 10th solar luminosities. That's a lot better than 3.828 times 10 to the 36 watts. You'll see more of this later, and we'll use these solar units all the time throughout everything in astronomy. You'll see them everywhere. And because we use them so much, it's important we got to know them really well. And if we want to know them really well, and we want to know how stars work and how they do what they do, we need to use these observable surface properties and well-known physics to extract how the bulk variables that are shown here change from the core to the surface. And we call this the study of stellar structure. It's important to note that nobody's ever been inside the sun, but even still, we have a very good idea of exactly what's going on. Any successful theory of stellar structure and evolution must explain the observed properties of stars. We will use this well-known physics and computer models to understand how these and other variables change as we go from the surface down to the core of the sun. So let's see how that looks. To understand how stars emit the light that we see, we need to learn about how energy transports through the sun. To start with, very simply, stars emit light because they're hot. Specifically, they're huge balls and spheres of extremely hot gas, and if it's hot enough, as we'll soon see, that gas is ionized and it becomes a plasma. This gas, or plasma, is dense enough that we cannot see to the core, therefore it's opaque. What we see at the surface is well approximated by a thermal blackbody emitter. That means the light and matter interact until they all have the same temperature at a given depth in the sun, and we'll see how they interact shortly. Since it's a thermal blackbody, it emits light from the surface because only at the surface, i.e. the photosphere, can energy in the form of light escape. We call that the sun's luminosity. The luminosity is the rate at which it's losing energy to space in every direction, not just towards us. Therefore, if the sun is to maintain the observed surface temperature and surface luminosity, it needs to replace that energy by somehow producing this energy deep in the core. Remember, we determined that the core temperature must be something like 15 million degrees. And where does that temperature come from? Just gravitational compression? This Kelvin-Helmholtz mechanism would only allow the sun to shine for about 30 million years. So something else must be going on. And we'll leave that till later. But it's important to note that the energy is sourced from deep below and escapes out through the photosphere and is continually replenished. So now we have to look at the basics of thermodynamics. And we have basically 4 laws. We call the 0th law of thermodynamics the first, second, and third laws. So we're going to use this idea of local thermodynamic equilibrium a lot in this particular lesson video. It just means that local thermodynamic equilibrium essentially means that for any bucket of gas inside the sun, any heat lost will be replaced by heat coming into that bucket. We also alluded to the second law, which simply states that heat always flows from hotter regions to cooler regions, which is what I was talking about roughly in just a second ago. You can use energy to pump from a cooler place to a hotter place, such as a refrigerator, but now you have to make an isolated system bigger and include the region around the refrigerator. There's just no getting around these laws. So that's what we got to do. It's like you always have to go from a hotter region to a cooler region. And if you're pumping to a refrigerator, then the region around the refrigerator is in general equilibrating, meaning it's all becoming one temperature. But for our purposes concerning the sun, the second law just means that the sun is getting hotter than space, so heat flows from the sun in the form of light. The sun is trying to cool off, and so we see the arrow of entropy is showing the direction of energy flow, that is, to space. As for the first law, we'll see that mass is converted to energy via fusion in the core. This conversion creates photons and neutrinos as well as kinetic energy of motion, and the photons themselves are scattered and absorbed and eventually thermalized into a black-body spectrum at the surface. And because there is energy transfer, the sun is losing energy. It emits 4 times 10 to the 26th joules per second. That would melt a block of ice 1 astronomical unit long with a square by 1 square mile in under a second. That's crazy. A star is therefore some physical object, so it does not have an infinite energy source. Therefore, it must eventually run out of energy. It must then change and then must die. The energy production is the star's vain attempt to beat gravity, and stellar evolution occurs because of this constant fight against the relentless pull of gravity. These laws of thermodynamics are just what the sun must do while it's engaged in this life and death struggle. Eventually it'll lose, though. So exactly how does energy get from the center of the sun to the photosphere? There are 3 ways to transport energy away from a heat source. The first is radiation, where energy is carried by photons or relativistic particles like neutrinos. Photons, as we learned in my atoms and light lectures, are packets of energy that interact with matter via the electromagnetic force. The photon's wavelength is inversely proportional to its energy, or rather, its frequency is proportional to its energy. Let's say a photon is made by some process. Then that photon goes from here to there, and in so doing, transfers its energy from here to there. Photons will obey the thermodynamics laws by traveling to a location where the photon energy density is lower than where it started. That's a very complicated statement, but basically it's about the intensity of light and how it drops off. And in fact, we can really think about it by saying, oh wait, what about that inverse square law that we talked about way, way, way long ago? That's basically the effect of that. It's diluting out and going to a place where it's less energy. Well, that's just how it dilutes. But basically, the photons are traveling from one place to another, and the energy is being transferred from this place to that place. Okay. Convection is the next thing we're looking at, which is the little bubbly thing in the middle. And let's say you heat a bubble of gas. If it's hotter than the surroundings, it'll be more buoyant and rise to a cooler location to release its energy. Okay? So this buoyancy is determined by pressure and density and temperature, among other things. So if you get a bulk motion of the gas, like a big cloud or a big volcanic gas wall, it'll go from below to above. The classic example is, of course, a boiling pot of water. The bubbles at the bottom rise to release their heat as steam at the top. But the sun is not a liquid. It's not a liquid anywhere, not even in the core. Nowhere is the sun a liquid. It is a gas, and more specifically, a plasma. This means the sun behaves more like Earth's clouds in the sky than Earth's oceans or a kitchen pot. To sum up, the stellar convection is when the energy is carried by bulk motions of the gas. Finally, we have conduction, where energy is carried by particle motions, vibrations, and collisions. Faster moving molecules, atoms, or ions collide and impart energy to slower ones. The faster motion is kinetic energy. The cooler places have atoms that are moving slowly, and hot places have fast-moving atoms. This process is really only important in crystalline structures where the atoms and ions are fixed in place, and therefore doesn't really have anything to do with the sun. So let's look at each of these transport mechanisms shortly. We'll need all of them. So now let's actually start to make a model of the star like the sun. So this is where the important point is. We have to model what the sun is doing in order to say how is energy transported from the center to the surface. And we'll approximate the sun as a happily perfect sphere with no burbles and glurbles like, oh, what about those prominences and flares and things? Oh, shh, just ignore that for now. So let's divide up the sun into concentric spherical shells, just like an onion. And of course, in this diagram, we only see circles, but yeah, get the idea, you know what I mean? Okay, next, we're going to define the volume of each shell. Each shell has a top and bottom radius with a thickness dr. This is, of course, the difference between the two spheres and the space between them. And the total volume of each shell, dv, or the d is little bit of volume, is equal to 4 pi times the radii squared difference. times dr, which is the radius difference between the two shells. And so remember, 4 pi r squared is the surface area of a sphere, and dr is a thickness. And so we can say, what's the surface area of the outer sphere and what's the surface area in the inner sphere? And so you take those areas and multiply it by, those are two areas and they're one's bigger than the other. And then you multiply it, you take their difference in the area, and you multiply it by the height that's difference between them, the radial difference, and that gives you a volume. And that's a very thin volume. But that's the volume that we're going to be using for this process. Now then we go a little further and make a grid out of all these shells with a stack of radial lines. Typically, you don't always need this, but you do need it for longitudinal flow. And you also will need it principally for longitudinal flow, but it helps us in this case to make this a little easier for some calculations. So let's break the grid apart and with the shells and make this stack of radial lines, right? Okay, so now we're going to make each box small enough that we can approximate each box as a cube. So it's important to note the volume of each box will be about the same for a given radius. It's not a real sphere, but these approximations are good for our purposes. And so what we're doing is we're kind of approximating the sun by a big stack of Lego bricks that make into a big sphere. So now we're going to zoom in and look at just one cell or Lego brick. So here we go. We'll assume that each one of these cells is in local thermodynamic equilibrium. And what is that? In thermodynamics, exchanges within a cell, usually called a system or so, and between the cell and the outside are controlled by variables that are shown. And so what do we have here? We've got a whole bunch of variables. We have m sub I, which is the mass of the shell. We got rho, which is the density, T for the temperature, P for the pressure, E for the energy creation, L for the luminosity, K is like a little kappa actually, is the opacity, dA is the surface area on the top and bottom of this cell, and R is the height up from the center, and dr is the height of the individual cell. So for example, temperature controls the exchange of heat. And in global thermodynamic equilibrium, that means the parameters are homogeneous throughout the entire system. But in local thermodynamic equilibrium, the parameters can vary in space and time, but they vary so slowly that for any point you can assume thermodynamic equilibrium in some neighborhood around that point. For this case, we only really care about the differences below or above each shell. And we're breaking it down into little cells just to make it a little clearer so we can understand what we mean by that. So what about rotation or magnetic fields or general relativity or supernovae or Cepheid variables? Okay, those are all really important things and we can get there. And in fact, if you really want to make people annoyed at an astronomy or physics conference, after they get this big discussion about it, just say, well, what about magnetic fields? That's why that's in there. And they'll cause eye rollings and so forth. But the really important thing is that we will get to these things, but we want to start simply and we want to start with a thing we can actually do. And we'll find that interestingly, that this relatively elementary treatment I'm about to talk about gets us to a long ways to things. We don't have to take into account relativistic effects. And we're not going to look at supernovae, which change in incredibly fast time periods, and Cepheid variables, which change huge amounts of the star with oscillations. But we'll eventually look at those things, but not yet. So let's see how all of these variables, m, rho, t, p, epsilon, L, and kappa, all interrelate. They're all incredibly important. So the first thing on our set, we're going to make a whole bunch of interrelated equations that relate all of these variables. So our first set of interrelated equations that bind the variables together into a system we're going to look at the mass. Let's see how when we pile stuff up onto a star into spherical shells, we have dm over dr, which is a change in mass as we change the radius. And that goes like the shell, or surface area of the given shell times the density. And the density will be the mass divided by the area and the height. And so that's what that dA dr is. So the volume of the density of a particular cell would be the area of the cell, would be the area times its height. And that's what the rho sub I is, which is the mass of an individual cell. But the important thing here, the really important thing is there's no big gaps in stars. There's absolutely none. There's not until you get to like a supernova, then you can have gaps, but that's only for the briefest fractions of a second. However, the sun, no big gaps. Normal stars, no big gaps. So again, dm is a change. Obviously, it's increasing because we're going up the star, and the mass would increase in mass for each little step in radius from the center to the surface. This mass gradient is dependent on the surface area of the shell times the density of the shell. And each little cell contributes a little bit of m sub I to the total mass of the shell at a given radius. So we have to think of an onion shell, and we're dividing the onion shells into their individual each shell into its individual cell. And that gives you the onion skin, right? So we're really using the onion skin analogy quite extensively in this thing. But let's keep going. Okay, so each little cell contributes a little bit of m sub I to the entire mass. Each cell has a density rho sub I that may have its own density. We're going to keep it super simple and say that at a given radius, it's homogeneous. The density is going to be the same here or there. We know that that's not truly the case because stars rotate, stars pulsate, there's always something moving. So, or at least not, well, if there's convection, there's something moving, and if there's pulsation, there's definitely something moving. And if there's rotation, there should be something moving. We're trying to keep the star static to keep things easy, okay? Simplicity, we're going to say that the density is uniform for the entire shell, not just an individual cell. Keep it easy. So the important thing is that the mass continuity equation says there's no big gaps and there's no island pockets of empty space in a star. And if you plunged into this star, you would never find at some like 100,000 miles down that there's this huge open space where no mass exists. That doesn't happen. Unlike some early science fiction novels where it's like, oh, go deep in the center of the earth and you get to big gaps and like huge ancient civilizations of lizard people live down there. That doesn't exist in the Earth, nor does it exist in the sun. The next equation is the equation of hydrostatic equilibrium, and that's a pressure gradient. How the pressure varies is a change in radius. The pressure is what supports the star against gravity, and the pressure is defined to be some force distributed over some surface area. And whatever the source of that pressure it must be resisting gravitational pull. And that's where the Newton's gravitational constant, that big G, comes in. The m sub star is the mass of the star's bulk beneath the current radius. So it's not strictly speaking one cell, it's the entire one cell, it's the entire shell. I'm just keeping the cell notation there for ease and understanding. Maybe it's a little confusing, but just we're looking at the entire shell. Okay, so r is the radius of the current shell, and m sub I, if you look in there, that's the mass of one little cell, and dA, di, is the area on the cell on the top and bottom, right? And dr is the height of that thing. So to make rho us out of rho sub I, we have to integrate over all the elements of each cell in the shell at that each cell in the shell at that given radius. Generally, they're all the same, but we're leaving the possibility of convective cells or horizontal flow or rotation. And you can stare at this equation and see you have a force per unit area per radial change, dr, on the right-hand side. And that's the same as the left-hand side. This all says that if the pressure balances the gravitational pull, then there are no bulk motions within the cell or the shell. And that's what we mean by hydrostatic equilibrium. We don't mean hydro as in water. The sun is not a liquid, but gases and plasmas are not solids and so can flow in a fluid fashion. But what we're looking at are gases that are not in motion and thus in equilibrium. So this is the statement of equilibrium where gas pressure equals the gravitational force that pulls it in. Okay, next we need something what's called an equation of state. And there's two parts, and this is part one, and we're going to use the ideal gas law. And we can justify using the ideal gas law even though the sun is not a monatomic gas, but rather it is an ionized gas or plasma. If we note that The particles aren't interacting chemically. They're just elastically colliding into each other, and they redistribute the kinetic energy. And so here in this equation, rho is again the mean mass, is the average mass density. M bar is the average mass of the particles, and mu or mu is the molecular weight. How you like that? It's a molecular weight. No, it's just the name of the variable. It's not, there's no molecules inside the sun except way at the surface. And we could get some, but most of them would be, tightly bound molecules and diatomic. But won't be many molecules, won't be any molecules below the photosphere, I guarantee. But molecular weight is just the name of mu. Now, m sub h is the mass of one hydrogen atom, v is the volume of the cell, n is the number of particles in the cell, k is the Boltzmann constant that we're familiar with, which has that number. Okay, so now first we're going to convert the mass density of the shell, of a mass density of a cell, into a number density by knowing the rough composition of the sun's interior. And we can know or measure or guess the average mass of the particles, but we'll state this in terms of the mass of the hydrogen atom. So mu is the mean molecular weight, and that can be calculated for a fully ionized gas that's composed of roughly 75% hydrogen or roughly 25% helium, and a little bit of other stuff. And that gives you 0.62 or thereabouts. And this compositional dependence will be tricky, and it does not stay constant throughout the sun. And we could make simplifications, we can, and using the Lane-Emden equation, and that gives us equations of state from polytropes. But that's advanced for this discussion, and I'll reserve that for some in-depth lecture, maybe in the future. Okay, for now, it's really good to note that this equation is a useful approximation to stellar interiors, but it's still not complete. To get the complete part, we need part 2, the pressure due to radiation. So photons possess momentum, and they can deliver an impulse to other particles during absorption or reflection. And that's what the P sub gamma equation is below, where the momentum is inversely, okay, this is terrible. Okay, P sub radiation is the pressure due to radiation, and that's equal to 1/3 times the radiation constant times the temperature to the 4th power. But little p sub gamma is the momentum of one photon given at a given wavelength, lambda, which is h is the Planck's constant. So I'm sorry, I used P for pressure and P for momentum, but welcome to physics. That's very, 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 very common. Okay, off we go. So we find that the momentum is inversely proportional to the wavelength, lambda, of a photon. This equation, this momentum, combined with the quantization of photon energies, was the foundation of the photoelectric effect that gave Einstein the Nobel Prize. So in sum, electromagnetic radiation results in another form of pressure. And in many astrophysical or solar situations, the pressure due to photons can actually exceed the pressure produced by the gas. So it's possible that the magnitude of force due to radiation can surpass the gravitational force, and that results in an overall expansion of the system. But this isn't happening in the sun today. It'll be like that in about 5 billion years, but not now. We will see that the pressure is, in general, an energy density. The units of the radiation constant, A, show this. The 4 Boltzmann constants show it's a thermal process, and the 3 pairs of H bars and Cs show that we're looking at a quantum processes associated with light. Thus, radiation pressure is only dependent on the temperature of the black body photon field. And that's where that factor 1/3 comes from the radiation pressure. So where does that 1/3 come from? Okay, well, it comes from vanishing the trace of the electromagnetic stress tensor, where the energy density is 3 times the pressure. Okay, so the energy density is actually the AT to the 4th, but the energy density is 3 times that pressure, whatever it is. And this is the electromagnetic stress tensor inside is that for an electromagnetic field. And why it's 1/3 is because there's one pressure from each Cartesian direction, x, y, and z, or left, right, backwards, forwards, up, and down. That's where the third comes from. So the energy density is equal to 3 times the pressure. So there's a long thing to actually derive this radiation pressure equation, but it's very common. You can go look it up if you wish, but most important thing is it's a significant radiation pressure is significant in stars. So the total equation of state that we have here, combining the two equations gives us a total equation of state that's applicable throughout the sun, from the core to the surface. Okay, this is what we need in order to relate. This directly relates a lot of variables that are inside of a given cell. Notice it doesn't include the luminosity, the opacity, or the which are the three things at the bottom: luminosity, K kappa opacity, and E epsilon energy production rate. So, but it relates all these macro variables, and we've seen these variables also at the surface of the sun. And the equation of state is the thing that binds them together. But let's get back to the thing at hand, which is energy production. And so energy has to be produced somewhere deep in the sun. And so I'm letting the cat out of the bag by saying it's nuclear fusion down in the core, and there's no contribution above it. So the equation that relates the luminosity, dl, meaning a little bit of luminosity, that's being produced in a shell that has a height of dr, to the energy produced per unit second per unit mass. There are contributions, one from sources like photons and gravitational contraction, and the other due to neutrinos. The neutrino contribution is negative because they don't interact and leave the sun without depositing the energy in any shell. So neutrinos interact, but they're part of the energy budget. It is produced by the nuclear fusion. They just leave, so they don't do anything to help out with the shells with the thermodynamic processes in the shell. So they're just gone, and they just loss of energy straight out. And we'll learn a lot about the exact method of fusion in the next lecture, which we'll talk about. Suffice it to say that nuclear fusion is the primary source of energy in all stars, and it's only produced in the core. And what is that thing? Proton-proton chain, CNO cycle, triple alpha. Well, just to predate to preview the other lecture, almost all of it's through a proton-proton chain with a small amount of CNO cycle and no triple alpha yet. Okay, so here they are in all their glory. These are the fusion reaction chains I was just talking about. And it's always fun to show these things. In the upper left, that's the proton-proton chain, which is the dominant method today. The CNO cycle on the right-hand side provides only a small amount. And the bottom left, the sun will do the triple alpha reaction when the hydrogen runs out in the sun's core, increases pressure and temperature to the point of being able to do this reaction. These are just the most common of the stellar nuclear fusion sequences, and I'll talk more about them in a future video. So now that we've set the stage for conditions for each shell in the sun, now we got to go back to energy transport. Oh my goodness, I've told this thing about energy transport, but now we're finally getting to it. There are three basic methods. We already talked about them. With a fun graphic on the right with a boiling pot of water, right? In the diagram, radiative transport is the light from infrared photons coming from a hot black body emitter, i.e. that is the heating element that's glowing red. And assuming the pot is not in direct contact with the element, but is held above. That's important. Otherwise, it would be conduction. So we're assuming it's radiating from the element to the pot, and the pot is not in contact. Don't do that in your kitchen because you'll burn yourself trying to hold up a boiling pot of water and you'll get burned too. But assuming the pot, so we got to assume that it's not it's not in contact. And when the infrared light, which is very intense, hits the pot, it heats the atoms and molecules of the pot. They then vibrate next to each other and conduct that energy, imparting their heat from hotter, faster vibrating molecules to the cooler atoms and molecules. That's the conduction. Convection arises when bubbles of water in the pot rise because they're hotter than their surroundings and thus become buoyant. Buoyant means lower density, and since they have lower density, they're going to go from a place where they're surrounded by high density, and they're low density, they're going to rise out of that high density to go to low density area. And once they do rise up, they release their heat as radiation, they cool, and then sink, forming a convective flow. Cooler gases are more dense as a result. Now these equations on the right, on the left-hand side, they describe each of these processes in stars. And in each case, The change in temperature as a function of radius is the transfer of heat from one shell of the sun to the next. And we're always going to be assuming that the core is hotter than the surface. So heat flows vertically in a star or radially, and these equations all show spherical symmetry. Let's look at each one now in turn. All right, first, conduction. I'm going to start off with conduction. Conduction is when heat is passed by vibrating atoms, atom to atom, or ion to ion, or molecule to molecule in a dense material. And this takes some time to do as heat is passed from atom to atom in a dense material from a hot to cool region. And so if you hold a metal tong by the handle and put its tip in a flame, over time that heat will be conducted from the tip of the metal tong up the handle, and you will feel it heat up. It doesn't happen immediately. And eventually, you'll have the same temperature as the flame of the fire, eventually. Conduction is only efficient when the densities are high, and that means the atoms or electrons are packed in close proximity to each other. And then K, here K, is the conductivity of the solid, not Boltzmann's constant. So now, why can't the metal in the tongs just radiate the heat? Because it's so dense that the materials can't easily, that light that is being produced by these vibrating atoms can't easily get from point to point. And in fact, there's a lot of photons bouncing around inside a heated tong in a fireplace, but the atomic and molecular vibrations carry more energy than the small photon field. So the atoms and molecules have so many ways of absorbing and emitting light, and it gets transformed into rotational, vibrational, or translational energy. Basically, this means that light at lower temperatures of infrared and microwave and radio wavelengths provide movement or kinetic energy. And so that feeling of heat in your hand when you pick up a hot pot or something next to a stove is because the atoms and molecules in your hand are now getting vibrated at the same rate as the vibrations of the handle of the pot. And then you got to burn. For conduction to be dominant, you need dense materials that can easily absorb light at many wavelengths, and it's not true for normal stars. But it does become true for white dwarfs and neutron stars, which is pretty cool. Anyway, enough about conduction. We don't use it. In the case of radiative energy transport, it's appropriate for the inner portion of the solar mass main sequence star and the outer envelope of a massive main sequence star. In all cases, the energy is carried away by photons radiating away from the heat source. All right, so we got a stack of equations here, and we're going to get through it to the bottom to show how we derive this. The first equation describes how photons diffuse through the star radiatively. F is the flux of energy from one shell, hotter, and which is to the one above, which is cooler. And strictly speaking, blue light is more energetic than red light. So, in a very astronomical sense, I got these two things reversed. But red, culturally, we could deem as hotter, and blue, culturally, we deem as cooler. So that's why I arranged it like that. But remember, T1, temperature 1 of the blue spots, is cooler than temperature 2, which is closer to the core. All right, so there's an energy flow through the cell and, of course, through the entire shell. And the net flux of energy is the difference between the two layers, Stefan-Boltzmann laws. So that's T2 to the fourth minus T1 to the fourth times sigma, right? So those are the two fluxes. And we can write that as a differential equation for small differences between the layers, and that's what we got on the top one. That's the top equation. So what's flux? Flux is the energy per second through an area. And if that energy is in the form of light and has a black body spectrum, then we can use that sigma t to the fourth power equation. Luminosity, by comparison, is the total energy per second emitted from some object, and the difference is subtle but important. Flux is power per unit area, and luminosity is how much total power. And so flux means you have to have some surface area either through which you're measuring. All right. With this in mind, the cell may absorb the light. And so the average distance a photon travels before being absorbed is the reciprocal of this kappa and rho. Kappa is now we're in the second equation. Kappa is the opacity of the material that the photons are passing through, and rho is the material's density. So the first part is an inverse length, or what we can call the chance of being absorbed per unit length. Strictly, it's the average density that the intensity of the photons drops by a factor of e, the exponential constant. But it's best thought of as a characteristic length of the photon's progress as it goes through the star. That is, its mean free path. So this mean free path gives the chance that a single photon will have one interaction traveling through such volume of gas. All right. Now, the third equation is the definition of flux through a spherical surface that we translate to luminosity. So assume you have a spherical surface that doesn't even have to be a star. It could just be some imaginary surface. And the flux through that imaginary surface, or the surface of a star, or whatever you want, and through any spherical surface is the luminosity from inside the surface divided by 4 pi r squared. And 4 pi r squared is the surface area of a sphere. All right, so that's where the third equation comes from. Now, the fourth one, and so if we take the two f's, right? The two f's, the derivative of t with respect to the radius, and collect those terms, we get the equation across the bottom. So remember, dr dt at the top equation is sigma t to the fourth. If we take the first derivative, we get 4t cubed sigma times dt dr. That's where that comes from. And there's the dt dr coming right out there. And if we combine these things together with the f, and we set the two fluxes together, we equate the f equals L, the luminosity divided by 4 pi r squared, right? And we set that equal to 4 sigma t to the third dt dr, and then we'll get the equation across the bottom. Now, the sigma can be looked at as, there's our 3 that we get. We get the 3 comes from the 3 comes from correct integration across all angles. That's where that would come from. But the 4 sigma over c is that really strange looking thing on the right, and that's the radiation constant that we would use. But sigma is from the Stefan-Boltzmann law. So the radiation constant, then if we use the radiation constant here, then the tilde across the top goes into exactly as opposed to approximately. All right. So now let's look at the drunken walk of an individual photon, because if we follow the average photon that's emitted in the core, its path outward to the surface is kind of slow, actually. So the photon leaves the core and then hits an electron or a proton within about a centimeter, and it gets scattered in some random direction. And so light travels really fast. And so it only travels zero point 0.1 nanoseconds before it hits another electron. And so therefore, it slowly staggers to the photosphere in a random walk, because that scattering is in a random direction. On average, then, it'll take about 200,000 years for a photon from the core to random walk its way to the surface. And in so doing, it'll also change its frequency and wavelength, because the interaction it'll have with electrons and protons and helium nuclei and so forth. So let's look at that equation across the bottom, which is what we I'm missing a negative, so I'll fix that later. Anyway, the equation across the bottom that we just derived. Okay, so it's divided up into those 3 parts, which are then combined into the final equation that's on the top. All right, so across the top, so the first part of these things describes how the photons diffuse through the star radiatively across the thing across the bottom. So that's how they diffuse through. And that diffusion speed is the speed of light c. And this is the speed at which the energy density changes propagate also for a given temperature gradient. And the energy density itself is actually A times A, which is that radiation constant, times the temperature to the fourth. And that's that scary looking thing off to the right. With the star being globally opaque throughout, we can assume that the photon field is a black body. And that's because, since it's opaque, all of the photons will interact with the electrons, and the electrons will also back interact with the photons as well. And so the photons and the electrons, and therefore the protons, will all come to the same temperature profile. All right. And then we can use and approximate some well-known equations using black bodies. Okay, so K is inside the radiation constant, that is Boltzmann's constant, which relates the temperature. And all those CH pairs, see the K to the fourth, there's 4 temperatures in there. So there's why we got a K to the fourth, because a K times a T is an energy. And the C squared and H bar squared, those things together, the speed of light and Planck's constant, we show that we're dealing with quanta of photons. So now let's take a look at this a little more distantly for just a second. The specific heat of per unit volume of anything is the specific heat C sub V is equal to the energy density per unit temperature, and that's 4AT cubed. So when we look at the 4AT cubed across the bottom, that is the specific heat per unit volume. And that is the energy density, how it changes if there's a slight change in temperature. So the energy density is that CAT cubed on the bottom. So it's a reciprocal of an energy density change, which is important. So the last part shows the luminosity in a spherical shell centered on the star's core. All right, so bottom of CAT to the third, that's an energy density. So that would be energy divided by density. And we have energy on the top, which is from the luminosity. And then we have kappa and rho is a density. So an energy density divided by a proper density, we then end up with our units being only a temperature as a temperature gradient, meaning a temperature as a function of distance, which was the dTdr on the left-hand side. So all of these units work out such that kappa times rho is an inverse length, right? So there's our inverse length across on the left-hand side. And the temperature, just a straight up temperature, is the CAT cubed on the bottom with a luminosity across the top. And that all gives us a temperature across the top, luminosity divided by an area, and then divided by an energy density times the propagation speed through which it's going. And that gives us a temperature. Those are the units of that. So in terms of unit analysis, so let's actually be more specific about it. The last part shows luminosity, and the whole equation is, of course, spherically symmetric. So we can read the bottom equation as saying, to show how the temperature changes with radius, we use the fact that all the luminosity in the form of light passes through a shell around the center, and it has to go through some thickness of material. And this thick shell absorbs the light, and it re-emits it, and that changes its energy density. This affects the entire field of photons as they rise and escape out of the photosphere. Right. In terms of unit analysis, the first term is an inverse length. The second term is an inverse of an energy per unit volume per temperature. And the third term is an energy per second per unit area. When you mash all this stuff together, you do get a temperature per unit length, a change in temperature per unit length, which is dTdr. So this drunken walk that we talked about means that the mean free path of the photon is not linear from the core to the surface because it's going through a changing energy density. And the mean free path, the L sub MFP, shows just how far it goes before it scatters off of something. So let's see why. So the opacity with kappa is a very complex function of the photon distribution. It's very complicated. But there are 3 dominant opacities in stellar interiors, specifically for the sun. The first is called Thomson scattering, and that's where a photon glances off an electron and changes its direction. This is the primary thing. This is the primary reason that photons take about 200,000 years to get to the photosphere from the core. Because of Thomson scattering. And there's so many electrons and they're so close together that a photon can only travel, like I stated before, about a centimeter before it hits another electron and then goes in some other direction randomly. And when these extremely energetic photons interact with electrons, they can impart some of their energy to the electron as part of the scattering process. And that means the photon changes frequency and the electron moves faster, and that gives us the Compton scattering that we see on the right. So that's an important mechanism that distributes that distributes the high energy photons made by the fusion reactions in the core, which are created at specific wavelengths into a thermalized black-body spectrum. These two things dominate. All right. Last, we have what's called free-free interaction. The cartoon shows the high-energy electron whizzing by the nucleus. As it does so, it changes direction and emits an X-ray photon. So this is called free-free Bremsstrahlung or braking radiation. So the electron, as it zips by the photon, will slow down. I mean the proton. As the electron zips by the proton, it'll slow down, and the energy it releases is an X-ray. And that can also go in reverse, which is really important. So you have an X-ray photon, and the electron's zooming by, and in the nearby presence of a proton, can absorb that X-ray photon and accelerate. And so the electron can gain energy and absorb the X-rays, and then can also emit them. So this process of this Bremsstrahlung, as well as the inverse Bremsstrahlung, I guess, free absorption and emission is the best way to talk about it. As the electron and the X-ray photon and the proton electron it can absorb or emit X-rays, and the electron can store that in the form of kinetic energy as it zips by. All right. This all means that the electron collides with a low energy photon and can bump it to a higher frequency. All these processes work together and they smear out the frequencies of these photons. And it serves to equalize the energy distributions of all the electrons, all the nuclei, and all the photons into a thermal black-body spectrum. And the actual functional form of this opacity, this kappa opacity, it really depends on the process in question. Some are strongly dependent on the temperature and others are not, with a lot of things in between. I guess I'm going to have to do a whole video just on this slide because there's quite a lot. However, the most important thing to think is that we're going to call this kappa for this particular thing that we're talking about in the solar interior. It's called the Rosalind mean opacity. And the Rosalind mean opacity is a specific kind of thing that involves these processes as well as many others. And it doesn't really care what the process is, the Rosalind mean opacity. It just says that there will be things that will absorb and re-emit the light at various frequencies, and you average that out over a large set of processes and wavelengths. Because sometimes, if you're not talking about scattering processes like the Thomson scattering or Compton scattering, well, Compton scattering is also very temperature dependent too. And so is free Bremsstrahlung and emission absorption. Those things, those thermal Bremsstrahlung can really be dependent on temperature as well. But we're talking also things that might be, well, atomic processes, which are not present in the core of the sun, will also create very strange opacities. But in general, the functional formality of kappa, the opacity, is extremely complicated. However, it can be simplified radically by noticing that the dominant things that are happening in the center of the sun below the surface are either Thomson scattering, Compton scattering, or this free, with the vast majority being this Thomson scattering. And that's why it takes so long for an individual photon to get out of the sun. All right. Energy in terms of convection. That's our third one. So energy for convection is carried from hotter regions to cooler regions by bulk buoyant motions of the gas. So we got these two little cloudy things. The red is going to be a hotter gas and the blue will be a cooler gas. Okay, fine. The hot gas near the bottom of the convection zone, it's going to heat up and it becomes hotter than its surroundings. And because it's hotter than its surroundings, its density decreases. And so if its density is lower, this cloud, then it will basically rise up to a lower density area to try to find an equilibrium point. And that becomes buoyant and it rises against gravity. And as it rises, it displaces cooler gases downward. And when it reaches the top, it gives away its form of heat. It gives up its heat in the form of light into space, and that radiates away. So that's where those photons are all about. So you get, strictly speaking, those photons that are coming out should be at where that arrow is, right? Not at the blue thing, but it cools off to form the blue lump, and then that blue lump then sinks. So there's a circular convective motion. This creates this convective flow, and we could call it boiling, and the convection in stars becomes really efficient when the gas and the hot layers of the star cannot pass radiation through effectively. And that's what this equation is. if when the specific heats of pressure and volume, okay, let's just go through. Let's go through it kind of quickly. Convective energy transport is usually modeled by mixing length theory. Okay, so here the gas in the star is containing some elements, these bubbles, and that nearly retain the temperature and the density and the pressure of the surroundings, but they move through the star as far as some length called the mixing length. And for a monatomic ideal gas, when the convection is adiabatic, meaning that the convective gas bubbles do not exchange any heat with their surroundings, then mixing length theory yields that equation for the adiabatic energy transport that we see, where gamma is for an ideal gas is the adiabatic index is the ratio of the specific heats of the gas, and that's for specific heat of pressure and specific heat of volume. Okay, with holding specific heat holding pressure fixed, specific heat holding volume fixed. For a fully ionized ideal gas, gamma is 5/3. So this is pretty much what we're going to be looking at, and that's in general. When the convection is not adiabatic, the true temperature gradient is not given by this equation. And in the sun, the convection at the base of the convection zone is adiabatic, but near the photosphere, that breaks down pretty quickly. So the mixing length, the theory of mixing lengths, contains two free parameters that have to be set to make the model work for the observations. So it's not really a rigorous mathematical formulation, so it's got to be kind of fixed in terms of observable parameters as well as computer modeling. But we can determine, interestingly, this gamma as a function of depth. That gamma, the ideal gas gamma, that's for an ideal gas, but the gamma in the equation itself, when it's closer to the surface, you can derive that from helioseismology. So what this for the convective energy transport the adiabatic energy transport or convective energy transport equation we see here shows is a gradient of temperature dTdr, and that's equal to some fraction 1 minus 1 over gamma, which is that funny thing that shows what the mixing length theory how the specific or the ratio of specific heats for an ideal gas, which is true deep in the star, is equal to the temperature divided by the pressure times the gradient of the pressure. So we have from before, remember we had a pressure and temperature relationship from the pressure and temperature relationship uh, from before, and that allows us to actually put these together with all the other equations. All right, so now we need to talk a little bit about thermal equilibrium in stars. A star is going to be in thermal equilibrium when the amount of energy generated in the core is balanced by the transport of that energy to the surface and it gets radiated away as starlight. So in thermal equilibrium, the surface of the star is, in the most general sense, not getting any hotter or cooler. Okay, so the core is, again, in the most general sense, also not getting hotter or cooler because there's continual energy generation in the core because of gravity. So gravity is pushing in, and that generates energy in the core to support against gravity. And this thermal equilibrium is a totally delicate balance. If more energy is generated than is required by the star's luminosity, then the excess energy makes the star expand. And if less energy is generated than is required, the star then contracts to make up for that in order to heat up the core. That means thermal equilibrium is an incredibly important and a central idea in the evolution of stars. So long as something is producing that heat in the core, and so the generation, how much energy is generated in the star's luminosity, then the thermal equilibrium stays in balance. And you can get more luminosity out of the star if you contract it. And if you collapse a star, you collapse the gas, and the core heats up. And if it heats up, it emits more energy. And if it emits more energy, then it expands and expands. And it'll push the star out a little bit. And so that means this is a really natural thermostat. And that's what I mean in the most general sense, these don't change. And of course, over the course of a billion or 100 million years or what have you, yes, this will change. But day to day, in the course of a human life, or course of 100 years, or 1,000 years, or 10,000 years, it's not going to be a big change. It's not going to be a big change. You have to wait to look at much longer timescales because the sun's going to live about 10 billion years or so, right? So since it's going to live about 10 billion years, you have to wait about a billion years in order to see some changes, or roughly 100 million years to see some changes. But it's important to always remember that gravity is always pulling on the stars, and that is ultimately, that's the thing in nature which causes everything to change. And so as gravity squeezes the star has to emit light in some way because it heats up in the core. And that forces the evolution of stars because stars have to change because luminosity means they're losing energy. And so therefore, something's got to happen down in the core to replenish the energy that is lost, and stars are finite objects, and therefore, as they use up their sources of energy, they must change. All right. And somehow energy is made, and in main sequence stars, that is hydrogen fusion into helium. The star contracts under the form of the hydrostatic thermostat. And if too much energy is produced, it expands, and energy generation then slows down. It'll cool off until gravitational pressure heats it up back again. The core cools because there's lack of fuel. The star compresses until it heats up and makes the particles move fast enough to find each other, to do some sort of fusion, to give off energy, to make it expand it again. All the while, the energy being produced goes from this hot place to that cool place, transported by radiation or convection, not conduction. And this thermal equilibrium stays true so long as there's an adequate fuel source. The hydrostatic equilibrium indicates that there's bulk motion of the star's interior as the material absorbs energy from the core and passes it along. That's hydrostatic equilibrium. It's like the movement of material. So nothing's moving inside of the star. Okay. Oh, deep inside the star, once you get below the convection zone, then it's just radiating. In general, stars are in both equilibria, both hydrostatic and thermal equilibrium, but only to a really good approximation. Approximately, as we've seen, the sun is dynamic. It has flares, it has prominences, coronal mass ejections, and so on. And that flow is actually small. That energy flow that we see from the surface is really small compared to the total bulk of the sun. And so, but this idea is completely violated when the sun starts to run out of hydrogen in the core to fuse. And that's when stuff really gets moving and it really changes. But we're going to have to wait for a few billion years. So make a note, tell your future self to go check it. Maybe somebody will resurrect our consciousnesses in 2 billion years to see what we thought about this. All right. If we take all of the equations that we saw together and pump them into a computer and using the surface parameters I talked about at the beginning of the video, as well as some bulk guesses for what the conditions are in the core, and then we can solve these equations simultaneously from the surface of the core and the core back to the surface in both directions. And we'll get some really crazy stack of numbers that show how each variable that we see in these equations change as you go from the core to the photosphere, to the surface. And these equations tell us the internal structure of the star. I mean, it looks complicated and it seems it, but it's actually incredibly simple. I made programs like these during my undergraduate days using 1988, 1989. Well, really? Yeah, 1988, 1989 computing technology. And so the output I got when I was back in college was stacks of paper with numbers on it. And it was kind of fun. And programs like these are really simple. I mean, look at these. We got what, 6 equations, right? And then some, wow, that's it, 6 equations. We got the hydrostatic equation, we've got the mass continuity, we've got radiative transport, we've got adiabatic transport, we've got luminosity, and of course, we've got the equations of state, the pressure equals the equation of state. So, and we've got an energy generation process down there. So those 7 things, that's all we really need. It's not like we're trying to figure out what's going on inside the cells or DNA, or mitochondria, the powerhouse of the cell. We're not trying to figure that out. Those are incredibly complex processes. DNA is insanely complex. Biological processes are far more complex than anything we see in the sun. And they can't be broken down into these kind of simple equations with any degree of ease that will make the good level of approximations that we get with stars. But stars, we can use these things. And this is how we can understand what's going on. So if you take all this stuff and look at surface properties, and we look specifically for the sun, we can actually look at some computing runs and see what the output look like. So here are some outputs for mass, luminosity, density, pressure, and temperature. And now I'm going to show you some solar profiles solar model profiles made by Kevin France at the University of Colorado. And these come from his website. If you just Google Kevin France at UC and solar modeling, you will see these. And these graphs are simultaneous numerical solutions of all of these equations made into graph form so that they're easy to kind of understand. So when you do a solar model like this, what you get is an enormous spreadsheet of tabular data as output. And you simply choose the columns from this thing. And it's going from the core to the surface, from 0 to 1. And that's what everything's been normalized, 0 to 1. That's what we see at the left-hand side. Well, across the bottom, 0 to 1, right? Radius divided by the solar radius, the total radius. And that's normalized to why we have radius across the bottom of each of these graphs. So you just choose the columns you want to present for clarity, and some authors put them all in one graph, and that can be interesting, but it can be confusing and tricky to read. So let's go through each one. Upper left, the mass and luminosity as a function of radius. As you can see, the mass fraction is the solid line, and the mass fraction shows that a lot of the mass, we've got 60% of the mass of the star, or well, more like 95% of the mass of the star is in the first 60% of the star. That's what the mass fraction says. And let's see, we're 50% of the mass of the star is, and down roughly 50% of the mass of the star, according to the solid line, is about 1/3 of the radius. So that's half the mass of the sun is down 1/3. And by the time we get to 80% of the radius of the sun, these are solar models, by the way. This is all one big solar model. And so by the time we get to 80% of the sun, we've gotten all the mass inside. So everything that we see from the surface of the sun, the photosphere, that's almost nothing of the sun. It's all the kind of surface fluff in a certain way. Now, the luminosity fraction is also printed there. And that's interesting because we can see that the luminosity, all of the luminosity gets generated inside the nearest 20%, the bottom 20%. By the time you get to 20% of the radius of the sun, the luminosity that's going to be generated has been generated. That's what that upper left graph means. Now we can go to the upper right graph, which is density as a function of radius. And we see that everything's going to be as a function of radius. The density is the highest in the core and drops to practically really very, very low density. Once you get out to about 50% the radius of the sun, or 40%, we can see that it's down to its lowest. It's down to basically surface level density at about 40% of the sun. So less than halfway out from the core of the sun, the density has dropped to roughly the surface of the sun. Roughly, very roughly. So, but the density is incredibly high in the core. That's important to remember. And now the temperature profile, though, doesn't drop. The temperature profile drops rapidly, but not as rapidly as the density. That's also important because remember, temperature is the thing that shows whether or not it's convective or radiative. And finally, off to the lower left is the pressure as a function of radius. And notice that is very similar to the density. So density and pressure are very, very similar with the pressure dropping off just a bit faster than the density. In fact, you can see that the pressure has dropped off almost completely away from its maximum amounts by about 40%. But the pressure is incredibly high in the center, in the core. And notice that the pressure also marks the luminosity. Where the highest density is and where the highest pressure is, that's where all the luminosity is. But the temperature doesn't do that. The temperature is just like, well, we're all hot and we're moving and stuff. Okay, so let's look at the next one set. Here we see the effect of the convection on the sun. About halfway out from the core, convection begins to become important and changes the slope of the radiative transport gradient. So remember we looked at the radiative transport equation? Right there's where it is. That's the pure radiative transport gradient, which is the yellow line. But once you say, oh, wait a second, we have to figure out what the effect of convection is on that. And that's where the blue comes in, is that the effect of convection starts at about halfway out the radius, and it gets that 5/3 value really quickly. See where it gets all of a sudden, boom, it becomes fully convective right at about 70% of the radius of the sun. And there's some mixture of radiative and convective deep in the core, but it's mostly radiative. It's just the radiative gradient is extremely disturbed by well, I shouldn't say it's convective in the core. It's not. The radiative transport is how photons are getting around because the density's too high for convection to occur. But convection onset occurs uh, very strongly at about 70%, and then it's like fully convective from about 70% of the radius of the sun to the surface, and it's fully convective for energy transport. So how is energy transport in the sun? As the question that begins from the very beginning of this video, this equation, this graph shows how it's transported. Where the yellow line is, it's dominantly radiative. Where the blue line is, it's dominant. Where it diverges from that, that's where it's dominantly convective. And deep down in the core where fusion reactions are happening, all bets are off. Great. Next. Here we see fusion reactions occurring in the sun. Okay, so we're looking at the energy production rate, which is on the left, and the luminosity fraction, which we saw already. Notice that we say that what is the energy production rate, which is that DLDR, and all of the energy production rate, all of it happens before 20% of the radius. And most of it, in fact, happens in the inner 10%, as you can see. And what luminosity fraction is like, what fraction of the luminosity has been generated inside that radius. That's what the right-hand graph means. So these units are in ergs per gram per second. So this is the specific energy production rate as opposed to ergs per second. It's ergs per gram per second. Makes it, that's okay. It folds in a bit of the density aspect to it. But we see that the energy generation is extraordinary near the core. And that's where all the processes happen. Now, above that, there are no new contributions. And so the conditions for fusion only exist deep in the core of the star. As a result of the fusion reactions of the core, we also see a depletion of hydrogen in the core and an increase in helium-4. Notice from these four things, these four graphs, this is a hydrogen fraction, helium-3, helium-4, and carbon. But helium-3 is 2 protons and 1 neutron. Helium-4 is 2 protons and 2 neutrons, and that's the fraction of each. And hydrogen is simply a proton. I don't think we're worried too much about deuterium because I think it gets eaten up immediately in this process. So notice that helium-4 is settling into the core and comprises almost 2/3 of the very center. So 2/3 of the very center of the sun is helium-4 with only about 1/3 being hydrogen. So hydrogen is depleted in the core. That's very important to think. And that's where it's been converted. So the intermediate product of the proton-proton chain is helium-3. And notice there's an excess abundance of that right above the core. And it's fully depleted in the core because of the proton-proton chain. But its presence above the core indicates that there's a boundary zone where conditions can be ripe for fusion, but it's not hot enough to fuse together the helium-3 nuclei, which is the final step of the proton-proton chain. So that spike is actually a really good definition for the boundary of the core. And finally, it's also interesting to note that there's some any residual carbon in the core has participated in the fusion and been converted to nitrogen, oxygen through some very temperature sensitive and extraordinarily low probability fusion reactions outside of the main proton-proton chain. So remember, the sun was formed with other elements besides hydrogen and helium, and they will participate in the fusion too, but at extraordinarily smaller rates. In the sun, right now, the CNO cycle is extremely rare, but it's doing just enough to deplete the carbon in this core of the sun. And if it were hot enough, and the rest of the cycle would complete and free up the carbon for more fusion. So once it gets hot enough in the sun, and it's later in its life, that fraction will change. And so the composition of the sun changes with time. Notice these are not the compositional fractions at the start, at the origin of the sun, nor will they be the compositional fractions for the sun in 5 billion years. So that's important to know. Next, how do we have energy transported finally in stars? In normal stars, it's a mix of radiation and convection, and these two processes convey the energy produced by fusion in the core to the surface. Now, we've seen in the sun that there's convection at the surface, as we've seen with solar flares and granulation and supergranulation and so forth. And radiative transfer is dominant deep inside the sun. Remember, these are processes. Radiative transfer is the process by which energy is transported, run the form of light between the core and the outer edge of that. It's going to try to, there will be radiative transport, but not as much once you get past about 2/3 of the way out from the center of the sun. Okay, only in we see that for small stars, only in the ultra dense stellar remnants of dead stars can we ever use conduction as an energy transport method. So normal stars do a mix of convection and radiation. And they always have significant temperature gradients from the core to the surface. But the compact remnants, like neutron stars and white dwarfs, have almost the exact same temperature from the core to the surface, which is really interesting. And it shouldn't be too surprising because these stars are really, really small, from the size of the Earth down to the size of a few kilometers across. Okay, so here we see some rough limits for the energy transport in main sequence stars. Low mass stars, stars less than about half the mass of the sun, are completely and fully convective. And their long lifetimes means that every nucleon will make many trips between the deep part in the core, right down the core, and the outer surface of the photosphere. They are truly churning pots. And solar mass type stars, between about half the mass of the sun, about 1.5 times the mass of the sun, they're predominantly radiative core and with convective outer envelopes. But once you get, and this shifts gradually, of course, you can think of it as deep radiative core that grows and grows and grows, but then gets followed again by a convective core. You can think of it as smoothly transitioning from left to right. So massive stars have convective cores and radiative outer envelopes. And we'll see in future lectures that massive stars are completely different than low mass stars. And this is one of the really important reasons why. The temperature inside the cores of massive stars is so very hot, and the temperature gradient is so great that it overcomes the radiative transport, and you get convective deep in the core. But for the sun, the temperature gradient isn't as great, isn't as steep, and so you do not get convective. You don't get convection. Anyway, this is how energy is transported in stars in general. And these are very, very loose. And of course, there are gradations, and we can say, oh, what is it like at a 0.7 solar mass star? What is it like at a 0.3? What is it like at a 2 solar mass star, a 7 solar mass, or 1.4? And of course, these are smooth. This is a smooth transition from left to right. Finally, let's just go right through this and look at all of these equations that we have together. They all work together to show how energy is transported in stars, and these equations are what we call stellar structure. These are stellar structure modeling equations that we can use to create computer programs that will actually model the interior of stars. And this is how we do it. This is how astronomers do this. Why else would people be learning Python like crazy and developing stellar interior models and so forth? They want to understand using these equations, and of course, many others, but this is an introduction to this concept. And these equations form the basis for what you wish to do when you want to know what's going on deep inside a star and how that energy gets transported from the surface, from the core to the surface, and how the star is going to behave. Because remember, as in science, we really want to understand measurables. And so there's measurables like pressure, there's mass, there's density, there's, as we see here, there's luminosity, there's temperature, and there's energy generation rates and massive hydrogen. All of these things combined together, those are measurable variables that have, and all of these equations then are their interrelationships. And so once we start to have a pretty good idea of what's in the core for general ideas, and once we have a very good idea of what we see on the surface, you make computer models using these equations, and you integrate the ideas both ways in a computer program, and then you iterate and iterate and iterate until you get a final solution. And that's what we saw with those graphs. That's exactly what it was. Anyway, hope you've enjoyed this, and please smash that subscribe button, and we'll see you soon. Oh, and by the way, I also want to thank my Patreon members, and here they are. Here's all my Patreon members who have been happily supporting me in this new effort of going out there. So thank you, Patreon subscribers, and please subscribe and mash that like button, and we'll see you next time.
Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. So this time we're continuing our exploration of the sun and the sun itself and looking at exactly what powers the sun and what makes it go. Last time we looked at thermodynamic equilibrium, we looked at hydrostatic equilibrium, and we learned that thermodynamic equilibrium leads to internal structure of the sun, and all these equations dictate that, where some locations inside the sun are convective and some are radiative, meaning that's how energy is transported. And which one dominates, whether it's radiative or convective, depends on the density and temperature and pressure at that location. And so the equations themselves dictate the internal structure. And the fact that the sun is emitting light and is emitting energy means that it must be changing. So how exactly is it changing? How long has it been alive? That's going to be the question for us today. So really, we're talking about energy production in the core of the sun. We're looking at that last equation from the stellar structure equations, little dl, how much in a little onion-sized shell around the center, how much luminosity, dl, is produced in a little shell of radius dr at a distance dr, r squared, r, and with the matter density of rho, which is that little p, and epsilon e is the total amount of radiative luminous energy, and E sub nu is the stuff that escapes by neutrinos. What's being lost? What's being seen? How do we get light from the sun, and how long has it been doing this? All right, big question. How long can the sun glow or shine or emit light? How long has it been doing it? How long can it do it? What is this lifespan of the sun? It's a really important question because it has bearings on pretty much everything else in the entire solar system, including evolution of life on Earth. So, in order to know how long the sun has been glowing, shining, and emitting light, we've got to know two things. We have to know how much internal heat is there in the sun, and how fast is that heat lost per second as sunlight. Well, the second one is simply the luminosity, and we can measure that relatively easily. It's really tricky to understand exactly what we mean by internal heat, though. So internal heat is a lot of different things. How can you get heat? Is it just simply hot and that just simply emits the heat? Is there some process that creates heat? And then that heat can be then transformed into light by various physical processes, and then that eventually makes its way to the surface and it gets lost. We saw last time that the process of light transmitting through the radiative zones actually takes about 250,000 years to get out from the core. That's how dense it is down there in the core, that it takes an extraordinarily long time for it to get out. But 250,000 years is a long time, so how old's the Earth and all that kind of stuff, and that's bearing upon this subject. So let's actually go back to the early part in the 1800s when people were developing the concepts of thermodynamics and and such things, because steam engines were being built, combustion engines were being built. And so there was a massive study going on all across Europe and the Americas about exactly how thermodynamics worked and how heat interrelated with work. And that's everything we really want to know. So by the end of in the early 19th century and by the late 19th century and the early 20th century, way up to the latter part of the 1900s, or the early part of the latter part of the 1900s, there are pretty much two ways that things could have sources of energy. One is chemical energy. You either burn something or you blow things up. And so that was fast oxidation of materials, or you put something on top of a hill and let it roll down that hill, which is gravitational potential energy, or you whack it with something. You take two things that are really far apart and let gravity pull them together, and then you make a big boom, and that would be like a meteorite hitting. So essentially, those are your two major energy sources that were known. And if you look at the economies and what people did back in the 19th century in order to do that, pretty much everything was reliant upon that. The electricity itself had not been developed until as a viable option for a very, very long time. So basically, burn stuff, blow stuff up, or drop things off hills. And that's how bread was made in water mills, because as a river would go by, that would turn a paddle, and that paddle would then turn a grindstone. And rather than make horses do it, you make the water going by a river do it. And so bakers used to be right by, and smithies, or using whoever needed power, steady, reliable power, would put a mill right on the waterfront of a river. Anyway, so that was what internal heat could be supplied in the 19th century. And people at the same time, other scientists at the same time, were studying how old the Earth was. And this was a fascinating study. And people were looking at how the Alps were overturned and folded, and the rocks were folded, and then the uplifted rocks in the Rocky Mountains in the American West. And even in Manhattan, if you go around the island of Manhattan, you find up in the northern areas, you see that the rocks are tilted, and they're layered and tilted, so things have been moved. And if you look at layered sediments, such as sandstones, or where fossils exist. But most classically, as one of the great things, is the beginning of geology, is by Jim Hutton in Scotland, and he hung off of a cliff above the ocean called Sychar Point in Scotland. And what Jim Hutton did is he looked at all the layers and found that inside the layers, just off this coast, this place called Sychar Point, he found that there were rocks that had been laid down by lava, then rotated, and then covered in sediment, then worn down, and then lifted straight out of the ocean hundreds of feet. And that process must have taken thousands upon thousands of years. And basically, these inclined rocks that occurred everywhere, and were there because of geologic processes, because nobody at the time was saying, okay, let's be logical about this. People didn't do this. Aliens or demons or devils or gods didn't do this, because that's boring. And to actually say, well, these creatures came down and gave us this weird look to the Earth, it's kind of silly, because that's, in a theologic sense, it's not that silly, because that's the nature of creation. But in a geologic sense, actually trying to understand it, you would come up against the idea of, well, okay, I can't prove that aliens came here or giant lizard people came and rooted around in the rocks and did that. So let's actually try to get a physical solution that makes sense, that keeps it simple, that we can justify. And that's called science. Everything else is either called theology, mysticism, or metaphysics. The problem is that when we looked at the age of things, it was found that the age of the sun was only about, if you think about chemical reactions, only keep the sun shining for a few thousand years. And if you whack the sun with a huge amount of meteorites, that keeps it going for almost 1,000,000 years. But so if you even imagine that every now and then the sun gets hit by something the size of Jupiter or something, then the sun could last a few million years. But geologists are finding that the Earth had to be hundreds of millions of years old, if not billions. So there was a fundamental conflict that was developing in the 1800s about how old the Earth was. And most geologists were saying, well, the Earth is older than the sun. And physicists who were, very smart, said, no, you geologists must be wrong. You're just looking at rocks. We're thinking thoughts. So this was pretty much the attitude that happened in the time. And there was a definite lack of reconciliation because one group sat around and thought deep thoughts in big places, and other people went stomping around in the Alps. So, in the 1800s, two physicists, Lord Kelvin and Lord von Helmholtz, developed an idea by which the sun could turn gravitational potential energy into light. So if you start with the sun, as we did in the previous lectures, in hydrostatic equilibrium, and with the internal pressure balancing the gravity, meaning it's hot enough in the center that gravity can't compress it, you then say, well, okay, fine. The light from the sun is luminosity, and that's radiated away, and it takes away some of the the sun's internal heat, which means that as the heat goes, it gets cooler inside the sun. And since it gets cooler, that allows it to compress, because a cool gas, if you take a hot gas and cool it, it compresses. So now it's got a lower internal pressure, which allows it to compress, which means the sun itself contracts and gets smaller physically. It's not just a big thing, it gets actually physically smaller, the radius gets smaller. And so then when the gravitation contraction compresses the sun, it then heats back up until it gets to balance position, and so it balances itself out, and the outward pressure increases because it's hotter now deep in the core, and then hydrostatic equilibrium is then reestablished. And this cycle then repeats, and the sun gets smaller and smaller by about 32 meters per year. 32 meters per year. Wow, that's actually it's an interesting and very quick compression, which leads to the sun only living for maybe 10 or 20 million years as its maximum. But this is called the Kelvin-Helmholtz mechanism for producing energy or producing light out of gravitational contraction. Basically turning heat into light, and you heat something up until it glows. And that's where the heat and light comes from, because you assume, as Kelvin and Helmholtz did, that all the heat gets converted into black body radiation, and all the energy of photons and light becomes unified inside of the sun because the sun's opaque. And since it's opaque, the light bounces around inside of the sun until it has the same temperature as the material, and the material and the light have the same temperature, so therefore it is a black body radiation, which is what is observed. So how long does it take? So you can't glow and contract forever in the power, and if it does power that, then we can assume that the gravitational potential energy, which is the gm sub sun squared over r, this r of sub sun. So this is the total amount of gravitational potential energy if you take all of the matter of the sun and spread it out to infinity, way out, and then just say, okay, now let's take all of this matter, pretend it was at infinity, and let it all fall together to form the sun. And so as it falls together, it loses energy. And that total amount of energy it can lose, going from infinity to as small a point as you like, is the gravitational potential energy. Take the current gravitational potential energy, which is the numerator of that equation, and divide it by the luminosity, the current luminosity of the sun, L sub sun. And that's the energy emitted per second. So this ratio says that the sun could only live for about 30 million years, which is nothing, which is really nothing. Very, very, very short time scale. But this is important for stellar, but if you think about it, this might be important for stellar formation, but not necessarily for keeping the sun alive forever. If this is the only thing that the sun or any star ever did, then stars could only live tens of millions or hundreds of millions of years at the most. So by the late 1800s, Kelvin and Helmholtz basically take a couple extra things. As the sun will shine for a little over 20 or 30 million years. And that it was even actually corroborated by Kelvin, because he went and looked at studies done at the difference in temperature between the surface of the Earth, or rocks at the surface of the Earth, and rocks deep in mines. And he assumed that the Earth was once completely molten. And if the Earth was once completely molten and cooled to its present temperature inside, he got an age of about 10 or 20 million years. And he said, it's a good estimate, so I'm on the right track. So the Earth's only a few tens of million years old. But geologists were saying, no, it's a lot older than that. It's about 2 or so billion years old. Kelvin and Helmholtz, from their high seat in academia wearing wonderful clothing, said geologists are wrong. Nature says you guys are wrong. And geologists said getting outside is nice because, nice day, get out of that place and go walk in the Alps and go look at the rocks. The problem is that not all of the physical processes that that nature did were known to Kelvin and Helmholtz at the time. They needed to be discovered. So let's take a second back and just say, let's take one of the great things that happened in the latter part of the 19th century, and that is the great industrial revolution because of the discovery and the use of coal-powered burning all across Europe. And let's pretend for a second that we've got a coal-powered sun. So if you burn a kilogram of just regular old brown coal, that's about 25 megajoules of energy. Remember, one joule per second is 1 watt. So this is about 25 megawatts. If you burned 1 kilogram of coal in 1 second, you would get 25 megawatts. So that's a lot of energy. And we have coal plants across the country and across the world because it does release a lot of energy. However, the sun's luminosity is a little bit brighter. It's about 4 times 10 to the 26 joules per second, or 4 times 10 to the 26 watts. And at a total amount of 25 megajoules per kilogram, you'd have to burn up almost 2 times 10 to the 19th kilograms of coal every second just to keep up with the sun's luminosity, if the sun is powered by coal. Now, since the Earth has a mass of 6 times 10 to the 24th kilograms, at that rate, you would burn an Earth-sized ball of coal in about 4 days and 8 hours. Now remember, about 1 million Earths fit inside the sun, so the mass of the sun is about 1 million times that of the Earth, so that gives you only about 4,000 years. Wait a second, that matches what those creationists are saying the age of the Earth is. Maybe they're right about something there. I don't know. But, don't tell them that because they might glom onto it. Anyway, just go talk to creationists and tell them that the coal could power the sun. That makes it only 4,000 years old. You'll have a lot of fun. Troll them massively if you wish. In any event, 4,000 years is the length that you get if you want to have a coal-powered sun, and it doesn't work because everything that we know makes the Earth much older than a few thousand years. Okay, back in 1896, Henri Becquerel was on the forefront of research, and in 1895, Wilhelm Röntgen had discovered X-rays. And what he'd done by looking at naturally fluorescent materials and minerals. So Becquerel was investigating these fluorescent minerals, meaning something made out of uranium. If you take pitchblende and you compress it, it emits light. So these are fluorescent minerals that he thought were glowing because irradiated by the sun. And so what he did is he thought, well, it must be getting light from the sun and converting it into this light, so it must be sunlight that's doing it. So what he did is he was going to go outside and take a whole bunch of photographic plates with potassium uranyl sulfate and wrapped it with black paper. And he was going to expose them to the sun and then go and see what was done and see what the images were. So he put something like a ring or some images on there to see what would be imaged on the sun. Unfortunately, the day he was going to do that, it was cloudy that day, and so he left it all wrapped up, and he went, oh, darn it, my photographic plates are ruined because it was a cloudy day. Kind of funny, because he wanted to expose it to the sun. But he left them wrapped in black paper, and he said, oh, what the heck, I'll expose them anyway. And even though they hadn't been exposed to the sun, he found that there were images of the objects that he had placed in with the black paper. And so therefore, the uranium itself had emitted radiation without any external source of energy like the sun or dropping rocks on top of it or like coal burning or something weird. So therefore, Becquerel discovered radioactivity. He discovered that a mineral actually emits light. So what he did then is he made an apparatus very similar, and people had learned a long time ago that there were different kinds of emissions from these objects, and this was the forefront of research in the latter part of the 19th century, is if you take a charged plate with a plus or minus on charged plate, or a strong magnetic field, and then you take your sample that's radioactive, and you put it inside a lead container so it all comes out a particular hole, and then you have a charged plate with a strong voltage, or you have a magnetic field. The alpha rays, which are positively charged nuclei, helium nuclei, they will bend towards the negatively charged plate in their path. And so they will veer off to up in this direction. And if they're beta rays, they're electrons. And so they will be attracted towards a positively charged plate. Notice how the alpha rays, though, go farther than the beta rays, and that's because alpha rays are helium nuclei, and as helium nuclei, they're made up of two protons and two neutrons, so they don't get affected as much, so their path is not changed. However, electrons are very, very light, much lighter than helium nuclei, so their path gets bent rather rapidly. Gamma rays, though, don't get bent by it. So what was discovered is that alpha rays are positively charged, beta rays are negatively charged, and gamma rays are not charged. And so they had these three different kinds of things, and they were based upon their electric charge. And this was part of the great discoveries of the latter part of the 19th century. All right, 1905, Einstein had his great year, and he published special relativity. And he found that mass and energy and special relativity are the same thing. And that's through the great equation E equals mc squared. And it says that it's possible to somehow transform matter to energy and energy to matter. And he basically said they're the same thing, and that's the nature of one of the discoveries of special relativity. So if you can somehow have a way of actually converting matter directly into energy or energy directly into matter, you can do this. So there's an equivalent amount of energy that resides in every piece of matter that it can be released to this large amount by multiplying it by c squared to get you the total amount of energy that's stored in the matter if it is converted completely into energy. That's what that means. So 1920, Sir Arthur Eddington examined someone else's previous measurements, F.W. Aston's measurements. Aston was measuring low mass elements like hydrogen, helium, lithium, beryllium, and so forth. And he noted that and Eddington noted that 4 protons have just as 0.7% of more mass than a single helium nucleus. So it's kind of funny because helium nuclei are 2 protons and 2 neutrons, but 4 protons have a little bit more mass than that, but a neutron's a little bit more massive than a proton. So what's going on that these things are actually, that a helium nucleus has less mass? So he said, let's say, do we take the Einstein's E equals mc squared, and he proposed then, let's take 4 protons, put them into one helium nucleus, and the remaining 0.7%, less than 1% of the mass, could be converted into energy. So Eddington said, well, what if you did this? If you converted it, then you'd have that. And he said that's a heck of a lot of energy, because if you take that if you have 1 gram of hydrogen, 1 gram, which is equivalent to the weight of a paper clip, in the internet era, well, there's no such thing as paper clips anymore in the internet era, so what? That might be like a sheet of paper or something, or half a sheet of paper is about 1 gram. So, paper, goodness, what? People even know what paper is because nobody does paper. Well, anyway, grams. A few receipts that you have to take when you go and use Apple Pay at a store or something. Anyway, 1 gram of hydrogen, if you convert it to helium, 0.07 or 7 milligrams is converted into energy, and that becomes 6 times 10 to the 11th joules. And now that's a lot of energy. That's so much energy you could lift 64,000 tons of rock to a height of 1 kilometer. That's how much energy you could do with that. So that is an incredibly explosive amount of energy that comes out of 1 gram of hydrogen. So Eddington said, well, this is a huge amount of energy. Maybe we can use this. And that was his publication called The Internal Constitution of Stars on October 20th of 1920. However, it wasn't accepted because one does not simply fuse 4 protons into a helium nucleus. And so how do you actually do that? It's really hard to do. 4 protons colliding at once is extremely unlikely. It was also shown that 2 protons together aren't stable because, well, they both have positive charged nuclei. So how do you get 2 things just to stick? And somehow, well, even if you do chance to get 4 protons together, somehow you got to turn 2 of the protons into neutrons. Where does that happen? And it's got to be extraordinarily hot with temperatures greater than 10 billion Kelvin to get them close enough to fuse together. So that's the 64,000 ton question. Well, actually 4 aspects to this. And so how do you fuse 4 hydrogen nuclei into a helium nucleus? And that notation that we see at the top there, the hydrogen nucleus, when we say 1 to the upper left, that means how many total numbers of particles there are in the nucleus. And then a 1H means it's just a proton. But 4He means 2 protons and 2 neutrons for a total of 4 particles. Whenever it says helium, it always means 2 protons. Now you can have one less neutron, so you can have helium-3, and you could even posit helium-5, but I believe that's extraordinarily unstable and doesn't exist in nature, as well as helium-2, which doesn't have any neutrons, which also doesn't exist in nature. So this is a very difficult thing to do. So let's look at the first thing. Trying to make them collide and stick is very tough. Why? Because 2 protons have an electrostatic repulsion. They are positive charges, so they repel. Like charges repel, opposites attract, just like that old Janet Jackson song, right? So electrostatic repulsion is so great that the temperature is so incredibly high that nothing can happen. So what do these 3 equations say? The U sub 2, 1 means let's take 2 protons, number 1 and number 2, that each have a charge Q. And Q is the electrostatic charge on a proton. The Q1 is the electrostatic charge on proton 1, and Q2 is the electrostatic charge on Q2. And D is their distance between them. Let's say it gets down to as close as 10 to the minus 15th meters. Let's say that's our D for distance. The 1 over 4 pi epsilon sub naught is just the way we convert charge and distance into potential energy, and that's what the U sub 21 is the potential energy of taking 2 protons, number 1 and number 2, and bringing them to a distance of 10 to the minus 15th meters from infinity. How much energy is created by that? What is the potential energy of them pushing apart? It's a pretty big energy. So then let's say, we can then say what a kinetic energy is, and we say, well, imagine that what we want to do is we want to get the kinetic energy high enough such that they can get to that potential energy, so that all of the potential energy is converted into kinetic energy. And what would the speed have to be of a proton in order for it to get that close? And that gives us a speed, a kinetic energy. And if we set that, if we say, well, that's the kinetic energy we wish to have, we find this an extremely fast pace. It's a very, very, very high speed. But then we want to actually say, well, if we convert then the potential energy into thermal energy, because thermal energy is a representation of the speeds of the particles, we then set the potential energy, U sub 2, 1, to the thermal energy of the gas. And so we'd say, well, what would the average temperature of all these protons have to be in order for them to get as close, to have the capacity to get as close as 10 to the minus 15th meters? And that ends up to be about 10 billion degrees, or 10 billion Kelvin, which is a pretty high number. And it didn't seem like at the time that anything could actually get them that close. So back in the early 20s, people thought, well, the temperature of the sun has to be on the order of 10 million degrees Kelvin, 10 million Kelvin, not 10 billion. So it's 1,000 times cooler than it needs to be. Well, George Gamow, who is pictured here, he's in his striking suit, was researching exactly, in 1928, was researching how subatomic particles escape from the nuclei of atoms, because, well, the discovery of radioactivity said we have alpha particles flying out, we have beta particles flying out, and they said, well, how do they get out of those nuclei? How do they leave the nuclei? So people understood that nuclei were being broken down and becoming lighter, so therefore chunks were missing. And they said, wow, there's a huge amount of energy that's coming out from these things. How do they get that energy, and how are they getting it, and where are they going? So they discovered that the amount of binding energy of a nucleus was extraordinarily large. In fact, it was too large for any random process to just say, now I'm out and gone. There was no classical way for things to bounce around inside the nucleus of an atom, thinking of it as like a hole in the ground, for them to bounce around laterally such they bounce around enough that they would pop out. So quantum mechanics comes to the rescue, and Gamow uses the recent ideas of quantum mechanics, which states that all particles are also waves and have a distinct wavelength. We can imagine that the barrier to get out is a finite one, meaning it has to have a certain amount of energy and is a certain barrier to leave the nucleus. And whatever that barrier is, we can approximate it by some block. And we say, imagine that the wave of the waveform of the alpha particle, for a brief moment, gets outside of the barrier, and just on the chance. So sometimes it whacks the barrier and it reflects off of it, and maybe some of the wave goes outside. But imagine if the entire wave, on the off chance, goes outside the barrier. Because it's a wave, it must be continuous. So if it does that, then it escapes. So that's called quantum tunneling. And quantum tunneling says there's an off chance probability, a distinct probability that it just simply goes past the barrier, which cannot happen in classical physics, but it can in quantum mechanics. And this idea allowed him to say, well, this is how things leave nuclei, and it worked. So then in 1929, just a year later, there was a couple of students, other researchers, Robert Decourt Atkinson and Fritz Houtermans, said, try to put it in the other direction. See if you can do it by putting protons together with protons. And they found that using the concept of quantum tunneling, you can actually have them merge together to form the nucleus that is formed of a proton and a proton. They can get them that close together at the lower temperatures that are known, the 10 million Kelvin, not the 10 billion Kelvin, using quantum tunneling. However, that was still an unstable nucleus of 2 protons. So that was good, but it's not the complete story. Well, and this is what we call the Gamow peak, which is a very important thing. And this is what he was talking about, and this is what the other two were talking about, which are talking about Gamow and Atkinson and Outermans were talking about, is that the Maxwellian distribution of the probability at the temperatures that we're talking about, say 10 million Kelvin, the probability that a proton has that energy is the red dash that's falling from the upper left down to the lower right. And so the higher the energy, the lower the probability it has that energy. That makes sense because it takes it's the highest energy things are rare. So the Maxwellian distribution is what you expect to have for a particular temperature when the protons are at that temperature. Some are hot, some have higher energy, and some have lower energy. They don't have exactly the same energy. There's a distribution, but very, very, very high energies are extremely rare. However, with higher and higher energies, the probability of actually penetrating the quantum tunneling barrier increases, and that's what the curve going to that increases to the right says. The higher the energy, the higher the chance that you actually get inside and stay. And so if you merge these two curves, you get what's called the Gamow peak, which means at a particular temperature, for a particular certain energies of protons can actually get in, and that they're roughly around 4 kT, which is the time, roughly 4 times the temperature, 4 times the Boltzmann constant. So it's going to be a very, very high temperature, but the probability that this happens is still extremely low. But it just shows that there is a merging place where there is an overlap between the probability that they get through that barrier, which is the penetration probability, and the actual distribution of energies inside of the protons, inside of a thermalized protons field. So there is a chance, and that's called the Gamow peak, and that chance is really tiny, but it's there. So how often do they actually get there? How tiny is that chance? Okay. So at the temperatures and densities in the sun, and you can actually calculate it out, you find that a proton, as it's whizzing around at the temperatures of 10 or so or 15 million Kelvin, goes about 3 millimeters before it collides with another proton. It's a very short distance. And they do that every 5 nanoseconds or so. So a typical one collides almost 200 million times every second. A proton goes 3 millimeters and whacks into the proton 200 million times every second in the center of the sun. A typical proton. There's a lot of protons in the center of the sun, so how often does this happen? Well, that's still not enough because the Gamow peak is very tiny. So it's still so rare that it's got to do 10 to the 25th collisions before it has, on average, before it has the chance to tunnel into the other proton and do the fusion dance. So it's an extraordinarily rare thing, and it's extremely temperature dependent. And if you push the temperature a little higher, then you get more and more and more, the penetration gets deeper and deeper. So that's pretty good. So quantum tunneling is extraordinarily rare, but at the temperature we're talking about, at 10 million Kelvin. But it's just enough to provide what's needed. And let's see how that happens. So what happens when they finally do stick? Okay, great. So now we've got a mechanism by which we can say they finally can stick. So nuclear fusion says that like charged nuclei got to get close enough in order to fuse, and they've got to be at this temperature, and they've got to have quantum tunneling. So let's see what we got. Let's say they get close and we got some quantum tunneling going on and protons smack together. So we got a proton smacking together, we got the little flash of light, and so what happens? Well, a whole bunch of stuff flies out. And we've got a neutrino flying out, a positron flying out, and a deuterium atom or a deuteron, not atom, but a nuclei flies out. And the existence of the positron, the existence of the neutrino, and the existence of the deuterium nucleus had to wait until later until it was actually confirmed. But let's see what we get. So a positron is an anti-electron, and that basically is the same thing as an electron with a positive charge. And if you look up what Richard Feynman says, you could actually even look at it as a positron as an electron going backwards in time, or a time-reflected electron. And that'll send you down a rabbit hole on the internet. But for our purposes, it is the same exact mass and it has an opposite charge. And every aspect about a positron is the opposite of an electron. So when an electron and a positron meet, they annihilate. All of the energy, all of the matter that was the positron and the electron is converted into energy, and that energy is in the form of light, and that light is in the form of a pair of gamma rays. So it goes, because that two need to come out because of momentum concerns, but there you have it. So you have a gamma ray that comes out, and so you've got light in the form of gamma rays of high energy photons, and those photons bounce around inside there and eventually scatter and reduce and break apart and become lower energy by the time they reach the surface. So that's a beginning for how light can be created inside the center of the sun. So let's look at another thing, a neutrino. Neutrinos don't interact with anything. They just go foop out of the sun. As soon as they're created, they leave the sun. They just don't interact with anything. They are neutral. They don't do anything. They're gone. And the last thing is the deuterium nucleus. So a deuterium nucleus is basically a heavy proton. So you take a proton and slap a neutron on it. And so now the neutron itself, the deuteron or deuterium nucleus, the symbol could also be called 2H because it's one proton, but there's two nuclei, two atomic particles in the nucleus, so it would be a 2H. You can also call it a D if you wish. So the next step then is to smack a deuterium nucleus onto a proton, and we've got something. So this is what Hans Bethe in 1939 published. His concept was, now you can't really make two hydrogen nuclei stick, and nobody could, because the major thing is what I just described was the creation of the deuterium nucleus utilizing the weak nuclear force interaction, which creates the anti-electron and the neutrino. So everybody else prior to his work had been saying, well, how can we force the two protons to stay together? And Hans Bethe said, no, how about the first thing we do is once they stick, that instantiates the weak nuclear force, and that makes it turn into a neutron. So now the new deuterium nucleus can now collide and do other things. And we had this whole series of steps. And there's Hans Bethe really smiling because when he did this, he received the Nobel Prize for his advancement in physics. I believe it was 1967 is when he was awarded that prize. I imagine this is his picture from that time. So what did he call? He called it the proton-proton chain. So the first step is you take two protons and smack them together to form a heavy hydrogen, which is a deuterium nucleus. And one of the pieces of output is an E+, or that is a positron or an anti-electron. And that mu sub E is an electron neutrino, or a neutrino associated with an electron. So that is the first step of the reaction. So basically this is a reaction chain. And so you take a proton and proton, smack them together, that's what the arrow indicates, and you get out a deuterium nucleus and a neutrino. And the neutrino indicates that the weak nuclear force has come into play. The gamma ray, the neutrino itself then becomes, of course, we just described how the neutrino, it leaves the town, but the anti-electron merges with electrons that happen to be around and becomes a number. It smacks into an electron and becomes a gamma ray photon. All right. So now the next step is, because the proton is now shielded, the deuterium nucleus is a proton and a neutron. That shields some of the positive charge of the proton in the deuterium nucleus. So almost immediately the proton and the deuterium nucleus collide because, well, it can kind of come in from the backside and smack the deuterium nucleus where the neutron is, and that forms light helium. So and then emits a gamma ray. So we can think of the helium nucleus as a light helium nucleus with 2 protons. That's what He stands for, which is helium nucleus. But it's got 3 particles in its nucleus, and so 2 protons and a neutron. But when it's created what we could call hot, and it's a resonant frequency, so it can absorb it at those temperatures. And basically it's created in an excited state, a nuclear excited state, and that allows it to emit a gamma ray. So it's very similar to the creating an excited state of an atom, like in the Bohr model, except there's no little orbits inside of a nucleus of an atom, of atomic nuclei. So there's just an excited state, and it emits a gamma ray. So now we've got 2 gamma rays that are being emitted, one from the first step and now one from the second step, and each of these things has to happen twice. So now we have 4 gamma rays that are being created. And then finally, we have the 2 light helium nuclei smack together, because now they can do that. But you have to have very high temperatures because there's positive charges, right? 4 positive charges have got to overcome it. And this is where the 10 million Kelvin thing comes into play. So now they've got to smack into each other. They form a helium nucleus, and the kinetic energy that comes out of them it releases 2 of the protons. They fall out of the nucleus, and you're left with a normal helium nucleus plus 2 protons coming out. So the only thing that we get out of here is we basically take the top 2 lines, do that twice, and you end up with the bottom line. So 6 protons go in, and 2 protons, and a helium nucleus comes out. So the net result is 4 protons in, 1 helium nucleus out, and some other stuff like light, anti-electrons, and neutrinos. That's the end result of the proton-proton chain, and that's what earned Hans Bethe the Nobel Prize. This proton-proton chain occurs about 10 to the 38th times every second in the core of the sun, and those times you see inside this diagram show roughly the average time it takes between an interaction. So it's very rare for the first step to happen. It's extraordinarily easy for the second step to happen, and it's not as hard for the third step to happen, but it happens pretty quick. This process every second converts about 4 times 10 to the 38th protons into helium nuclei every second, which means that about 6 times 10 to the 11th, or 600 billion kilograms of hydrogen is converted into pure energy every second. That's interesting. That's really interesting. That works out to be about 4 million metric tons, and that's or 100 billion megatons of TNT. That's a lot. So this is an enormous amount of energy. This process can actually duplicate the output of the sun, which is about 4 times 10 to the 26th watts, which is an enormous, enormous amount of energy. So that's how we know that what's going on in the center of the sun. So we can take this theoretical construct and see how much energy is in there. And we say, does this really happen? And how big a volume is this happening in? We say, okay, the size of the core of the sun, I mean, that sounds like a lot, right? 10 times 10 to the 38th times each second. That's a big number. 10 to the 38th is big, but it's spread out. So if we then say how much it's being done over the volume of the core of the sun, it's pretty crazy. You say, well, how much power is being produced in the volume of the sun? You say the total power output works out to be about 275 or 276 watts per cubic meter. Okay, what's 276 watts per cubic meter? That's like 300 watt light bulbs in a large U-Haul box. So that's not a lot of power, actually, per cubic meter. And that's about the metabolism of a lizard. So it's kind of funny. The total output of the sun in the core, averaged out over the volume of the core, is really, 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 really small. That makes it kind of fun. So the tremendous power output is because the sun is enormously large, not because it's providing a lot of power. So the volume in which this can occur is enormous. But if we then think about what this is like, the largest nuclear explosion ever done by humanity was in 1961. It was the Tsar Bomba that was detonated by the Soviet Union in 1961. They were originally going to do a 100 megaton nuclear blast. They made it 50 because they were scared. And that is basically 1% of what happens in the sun's core for 39 nanoseconds. That's crazy. So the blast was caused huge damage up 600 miles away. It could be seen for it could be the blast was felt 1,000 miles away. Every second, the sun does this 100 billion times. That's an enormous output of energy, and it's very good that the United States and Soviet Union and everybody's trying to dial down the nuclear bombs because they destroy lots of things, and it's better to be alive than dead. Thank you for not blowing those up over everything, guys. So the proton-proton chain is a way of actually getting, so the mass difference is extraordinarily small. Is that enough to make the sun shine for a very, very long time? The mass difference is tiny. That's called the binding energy of the nucleus. It's a tiny amount of energy that's released, and there's a huge amount that's happening. But is that enough energy to make the sun last long? So let's actually analyze it. Oh, but first, there's another process that we can use called the CNO cycle, which uses carbon, nitrogen, and oxygen as a catalyst. I'll let you pause this and go over it if you wish to. But essentially, that stars like the sun don't do this. The sun only does this for a little bit of it, but if for stars that are just a bit more massive, it accounts for a huge amount of the process of the sun. The proton-proton chain is for stars like the mass of the sun or smaller, and any stars that are even slightly more massive than the sun, this is the dominant path for fusion. In any event, so the lifetime of the sun, how much gets converted? So it's 0.7% of the material gets converted into energy. So if we took the entire mass of the sun and converted it into energy and divided by its luminosity, that would give us about 100 billion years, which is interesting. But the sun will only participate because it's not convective down at the core, it's radiative down at the core, because we know that from stellar structure equations, that so only 10% of the mass of the sun participates in this. So since only 10% of the mass of the sun participates in this thing, then it reduces to about 10 billion years, and boom, there we have it. The total age of the sun can be about 10 billion years, and the age of the Earth fits into that, and we know the age of the Earth from meteorites and from other things to be about 4.5 billion years, so therefore, but the total age of the sun is much longer than the age of the Earth, and boom, we've got it. Nature, therefore, is revealed to us as us mere mortals, because it's just an amazing amount of stuff. 4 million tons of matter is converted into energy every second. It's turned into energy, completely gone. The mass becomes energy. And so modern estimates of radioactive dating give about 4.6 billion years. If we look at meteorites such as calcium aluminum inclusions inside of meteorites that fall, specifically one of the great falls that happened in 1968, called the Allende meteorite, which happened in Mexico. That meteorite fall gave us huge amounts of data about the age of the solar system, and we now know the age of the solar system is about 4.567 billion years old, and that gives us a good time. So the age of the solar system is about half the total fusion lifetime of the sun, so therefore the sun can live for about 5 billion more years. So stars shine because they're hot, and to stay hot, they make up for the energy lost. They have to make it up for it. And there's two ways. First, the gravitational contraction, which still does occur, but nuclear fusion keeps it hotter because now we have a pathway in order to get energy out of the sun. And that nuclear fusion solves the age problem that came up with in the middle of the 19th century and would have made Lord Kelvin shake his head. That's what we've got, the age of the sun. And let's see, so main sequence stars, we discussed this before. Wow, we talked, what are main sequence stars? Well, like the sun, they rely on the proton-proton chain, but more massive stars with much higher core temperatures do the CNO cycle. Here's an interesting question, though. Why doesn't the sun explode? Well, the fusion reactions are extraordinarily temperature dependent. And so think about it this way. If you increase the temperature of the core, well, the nuclei move faster. If they move faster, then they stretch into the gamma peak. The peak goes faster, which means that they quantum tunnel more frequently. If they quantum tunnel more frequently, fusion occurs more frequently. So if you have higher temperature, you have more fusion. But fusion, as we know, creates light. And if it creates light, it creates energy. And that energy then goes into making the core hotter. So if it's going hotter, that should lead to even more fusion. So why don't stars explode? Like big bombs. Why don't they go out of control? That's an interesting question. So there's a thermostat. Again, we go back to hydrostatic and thermodynamic equilibrium, and we say when the core heats up, that leads to a higher pressure. The higher pressure means that the whole core expands against gravity, and that cools the core, which then slows the rate of fusion. Now, if it runs a little slow because stuff's running out or what have you, the core cools, which leads to a lower pressure. Then all of a sudden, gravity pulls things together, pulls it, makes it contract, and then that heats the core. Ideal gas law again, because PV nRT, right? So the total amount of material gets compressed. And if it gets compressed, it heats more, contraction heats it, and increases the rate of fusion. That's a thermostat. That makes it so it cannot be a runaway explosion. So it doesn't happen. Also, it's a fact that quantum tunneling is extraordinarily rare to begin with, so actually getting the first reaction is rare, so you really have to push very hard. But the dominant thing is the hydrostatic thermostat, because the core of the sun can actually respond to pressure waves due to like waves of pressure that happen on top of it. And that's a rather rapid process. So in sum, energy is generated by nuclear fusion in the core. So it's controlled by a hydrostatic thermostat and regulated by the advancement of the quantum tunneling, which is actually what allows to occur. So the energy is then transported to the surface by convection and radiation processes in normal stars, and we haven't talked about white dwarfs yet, but we will, and you can go Google around if you wish. But the energy generation is called thermal equilibrium. Energy is created, it makes its way to the surface, it's radiated, so more energy must be created because it's being radiated. And then hydrostatic equilibrium says things aren't sloshing around really hard, or more specifically, hydrostatic equilibrium says if you decrease the pressure, you compress. If you increase the temperature, you expand, and so you decrease your temperature. So these two sets of equilibria merge together, utilizing the energy sources of nuclear fusion and to some tiny extent gravitational collapse in order to generate energy in the star, in our sun. So that's how the sun shines. The sun shines through fusion in the core, and it can live for 10 billion years. Not 6,000, 10 billion years before it runs out. Fascinating stuff. And that shows, and all of these things are basics of modern physics. And that makes the sun a core area where we can study and test the nature and understanding of particle physics as well. Next time we'll see exactly how that went haywire just a little bit. So, see you soon.
Hello, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. We're going to finish off the sun this time. We've been talking extensively about the sun in the last few lectures of this module, and we've talked about what's happening down in the core, the surface prominences, solar flares, and everything, and how energy gets transferred inside the sun from the core to the surface. But a big question remains: how do we know that fusion is truly occurring in the core of the sun? That's a really important question, and the answer involved an incredible amount of detective work that happened in the latter part of the 20th century. Neutrinos are theorized to be created in copious quantities by nuclear fusion reactions, but they're notoriously difficult to observe. It's by finally observing these that we can truly understand what's going on in the core of the sun. Incidentally, this is a great example of the way of science. We'll see that there's this back and forth process of explaining phenomena. You start with some explanatory idea, which requires some new experiment, which then gives new phenomena, which then need to be explained and tested. This is kind of check my work back and forth, is a hallmark of good science. It is also this willingness to adjust your ideas to fit reality, and not the other way around, that makes for good science. So let's go back to the equations of stellar structure to see how stars work. The core of the sun is an extraordinarily dense place. It's also extraordinarily hot and under extraordinary pressure. Outside of the core, we posit that no energy is being produced, other than through the Kelvin-Helmholtz mechanism of gravitational contraction, but that doesn't yield much energy. Combining all these equations together computationally, we conclude that the core of the sun has to be extraordinarily hot, around 15 million Kelvin. That should be hot enough, given quantum tunneling through the electrostatic barrier, that fusion reactions should occur in the core of the sun. Looking at the last equation, that dl/dr, we know that the reactions of the proton-proton chain, which is the little diagram in the lower right, we then expect the core of the luminosity to be extraordinarily large. The epsilon without a subscript is the energy created per second per particle by some material, here hydrogen fusion, in the form of gamma rays, and kinetic energy to heat the core. The epsilon sub nu is the energy generated from the form of neutrinos, which doesn't help to heat the core, but just zips out and leaves the scene. It is this luminosity due to neutrinos that we want to look for. So again, what are neutrinos? Neutrinos are fundamental, neutral, subatomic particles. They barely interact with anything. They also have a tiny but not well-known mass, and in fact are thought to be massless until only recently. They travel at very close to the speed of light, but not quite because of their tiny mass. They don't interact at all via the electromagnetic force or the strong nuclear force. They don't have an electric charge. The name itself, neutrino, means little neutral one, because they don't carry an electric charge, unlike the proton and the electron. And so they only interact with other particles through the weak nuclear force. Gravity, sure, but their masses are small, so they don't do much with that except cosmologically. Therefore, they can pass through an enormous amount of material without interacting with anything. A block of lead, 1 parsec thick, for example. They can go straight through that and not see a single atom of lead. So when neutrinos are created, therefore, at least we think they're created by fusion in the core of the sun, and every theory about nuclear fusion says they should be created, and if they are, they would simply stream out of the sun at or near the speed of light unimpeded. So what do we mean by fundamental particles? Here we see a diagram of the standard model of particle physics, together with the 6 quarks, 6 leptons, 4 force carriers, and 1 fundamental interaction. This all makes up the standard model of particle physics and comprises all of what we know about matter. These are the building blocks of all matter. Each of these 17 things is considered to be a fundamental particle, meaning they can't be broken down any further. And we see that there's 3 generations of fermions of matter. There are 3 different kinds of matter, and the most familiar are things that are constructed out of the first generation. Up and down quarks, when combined together in the right way, give either neutrons or protons, as we see in my little diagram. We also see electrons and neutrinos. So that first generation of matter is pretty much everything. Well, not pictured here are the antiparticles. So there's an anti-electron, otherwise known as a positron, and an electron antineutrino, and an up antiquark, and so on. Antiparticles have the opposite charge, parity, and time properties, but are otherwise identical to their normal matter counterparts. Our universe is dominated by normal matter, with antimatter created by various processes, and why that is, I'll leave to my upcoming lectures on cosmology. At the bottom are the leptons, and the one we're concerned about is the electron neutrino. So if a proton is converted into a neutron, or a neutron is converted into a proton, an electron antineutrino is involved via the W- boson. Typically in particle physics, a little bar over the symbol for a particle is its antiparticle. And I've demonstrated this in 2 ways, one with a funny cartoon I made, and the other with a standard Feynman diagram. The other generations of matter, which are charm and strange and top and bottom, quarks, have similar weak interactions via the muon and tau neutrinos and muon and tau leptons, but they don't create things like protons and neutrons. So we're going to ignore them for now, and we justify it in doing that because, well, that's not really important to the process. We don't think of any kinds of things like protons and neutrons created out of these quarks. So there's not much of them in the universe. Importantly, though, there are 3 different kinds of neutrinos, the electron, muon, and tau neutrinos, each one corresponding to its own lepton. Over there on the right-hand side, those are the force carriers. So you've got the photon for the electromagnetic interaction, the gluon for the strong interaction, and 2 more bosons for the weak interaction. These things and these ideas you would encounter extensively if you went to graduate school for particle physics. Armed with the idea that there's up and down quarks, and they make protons and neutrons, and the electrons pair with the electron neutrinos, let's a little bit more about the history of how it was found, how these neutrinos were found to be coming from the sun. So there are three different kinds of radioactive decay. First is the alpha decay, in which a helium nucleus emerges from the nucleus of an atom. A helium nucleus is also called an alpha particle. Second, beta decay, in which a proton is seemingly exchanged with a neutron and an electron emerges. The electron is also called a beta particle. Third, gamma decay, in which a high-energy photon emerges. Gamma ray photons are very high-energy photons. While the alpha decay is easily understood as a chunk of a nucleus falling out, and the gamma decay is understood as energy in the form of light escaping the nucleus, the beta decay seems odd. Ostensibly, there shouldn't be any electrons in the nucleus of an atom, and that was shown to be the case in 1913 with Bohr's model of the atom, which explained Rutherford's experimental data, which refuted Thomson's plum pudding model of the atom. So, why would an electron fall out of a place where it doesn't exist? So the neutrino was postulated first by Wolfgang Pauli in 1930 to explain how beta decay could conserve energy, momentum, and angular momentum. And Pauli hypothesized an undetected particle that was emitted from the nucleus together with the electron, or the beta particle, in the process of a beta decay. He called it a neutron. In 1932, James Chadwick discovered a much more massive neutral nuclear particle, and he named it a neutron also. So for a short while, we had two different kinds of particles with the same name, and the word neutrino was first used publicly by Enrico Fermi during conferences in 1932 and 33. And during his second conference, Pauli also used the name, and the name, the Italian equivalent of little neutral one, was coined by Edoardo Amaldi during a conversation he had with Fermi in the 1932 conference. And they were trying to distinguish between this light little neutral particle and Chadwick's heavy neutron. Pauli believed the neutrino was completely without mass. This idea of a massless neutrino was not overthrown until the solution of the solar neutrino problem, which showed that they had very, very tiny masses. In 1934, Fermi came up with a theory of beta decay. Chadwick's large neutral particle could decay into a proton, electron, and a smaller neutral particle, which we now call an electron antineutrino, via the reaction shown in the middle. Fermi's work unified Pauli's neutrino with Paul Dirac's positron and Werner Heisenberg's neutron-proton models to give a solid basis for future experimental work. And that was their goal. It's like, well, there must be something here, so let's figure out a way to make it observable. In 1936, the second lepton, the muon, was discovered by Carl Anderson and Seth Nettermeyer at Caltech while they were studying cosmic radiation. And they found it because due to the fact that muon trajectories in a magnetic field were really different from electrons and other known particles. And it was supposed, because of the trajectory change, that their mass was much greater than that of the electrons, but smaller than the protons, which is about 200 times that of the electron. Well, this new lepton led Isidore Isaac Rabi to say, who ordered that? And so that particular thing has made its way through all of physics. The tau lepton wouldn't be discovered until the 1970s by Martin Lewis Pearl using the Stanford Linear Accelerator and Lawrence Berkeley National Lab equipment when they found some odd events involving the positron-electron annihilation. They had to posit a new lepton and its antilepton in order to take into account the observed particle reactions. But let's take it back a bit. Initially, Fermi, Pauli, and others thought neutrinos were massless and undetectable. And in 1941, the muon was shown to decay into one single electron, and since nothing else could be seen, the physicists suspected that a new kind of radioactive decay that yielded a new neutrino had been found. A big mind in early particle physics, Bruno Pontecorvo, worked on the idea of neutrinos' detectability. In 1945, Pontecorvo noted that a neutrino striking a chlorine nucleus could transform it into an unstable argon-37 that emits an electron via beta decay with a 34-day half-life. This allowed for the idea of the neutrino's direct detection. Next, Pontecorvo suggested in 1957 that neutrinos might oscillate, change from one type to another because of their difference in mass, and we'll see why shortly. In 1959, Pontecorvo further showed that neutrinos that were produced in decays of particles from an accelerator could be observed with really large detectors, and proposed an experiment to find out if electrons and muon neutrinos differ from each other. The eventual discovery of the neutrino oscillations by the Super Kamiokande experiment in Japan was a triumph for Pontecorvo's ideas, but it came about a decade after he died. So let's see how neutrinos are produced. Remember in a previous lecture, I talked about the proton-proton chain. Soon after the muon was discovered, Hans Bethe, in 1939, published his paper that completed the details by which stars fuse hydrogen into helium. And this is the proton-proton chain. His big breakthrough was to examine the step that created deuterium and making it into a series of other steps after that. The first and most important step was the formation of deuterium. When deuterium is formed, an inverse beta decay happens. A proton's quarks interact with the weak nuclear force, changing an up quark to a down quark. In so doing, a neutron, an anti-electron, and an electron neutrino are formed. The anti-electron in that beta plus is that beta plus that's scooting off, which immediately hits an electron, annihilates, and creates two gamma ray photons. The neutrino is that little V kind of thing. The neutrino, as per Bethe, doesn't notice any of the high density of the sun's core and simply departs at nearly the speed of light. So, if the proton-proton chain is happening, then neutrinos should be streaming out a lot. How much? A lot. To account for the luminosity that we see of the sun, this reaction has to happen 10 to the 38th times each second. This is an enormous amount. Wouldn't we run out of protons at that rate? From a previous lecture, we learned that about a third of the mass of the sun is in its core. Making the lightly bad assumption that it's made up all of protons, then we get that there's about 10 to the 56th protons in the core. Since if you take 10 to the 56th and divide it by 10 to the 38th, you get about 10 to the 18th. And that gives us about the guess, a pretty good guess, as to the lifetime of the proton-proton chain in the sun. And since 10 to the 18th seconds is about 10 billion years, well, that's a lot of stuff down there in the core of the sun. The sun is really, really big. So if 2 times 10 to the 38th neutrinos escape from the sun every second, and if we think of them as spread out evenly, then they come out in every direction randomly, then they should be distributed evenly over the surface of a sphere centered on the sun. If they distribute over the sphere, then how many neutrinos go through each square centimeter at a distance of 1 astronomical unit? We expect to see over 60 billion neutrinos pass through every square centimeter on the surface of the Earth. That means if you hold your thumbnail towards the sun, every second, 60 billion neutrinos go through your thumbnail. Each second. That's pretty crazy. So imagine there's a number of skeptics that say, really, 60 billion neutrinos coming from the sun through your thumbnail every second? And that's for every thumbnail positioned at 1 astronomical unit in any direction from the sun? Okay, that's a lot. But where does that number actually come from? Well, remember we used the equations of stellar structure along with the reaction probability of the proton-proton chain, and you plug that all into computer simulations. These are really well known and really well understood physics and really well understood computer simulations, and they take as their input the bulk properties of the sun, like its total mass, observed luminosity, and surface temperature. We take all these surface bulk conditions and ask what would produce those outputs down in the core. And from my video on energy transport and stellar structure, we can run those simulations from the surface to the core and the core to the surface and back and forth towards each other until you get a good model that converges for both directions. And you get that convergence, we use the fact that the sun is really old and in thermal and dynamic equilibrium in the broadest senses. Basically, whatever energy is leaking out from the surface has to be replenished at the center. Now, it's hard to detect these neutrinos, but they are part of the energy budget that's coming out of the core and a required output of the proton-proton chain. And so because of this process, you can make a very robust set of predictions, and specifically about what the energies of the neutrinos are, not just that there are neutrinos, but how much energy that they have as they come out and that they take with them. We can then arm ourselves with this prediction of how many neutrinos from the postulate that nuclear fusion powers the sun and go look for them. So the hunt was on, but the detection of neutrinos is very difficult. Researchers understood that they needed to use a huge amount of some very heavy materials, such as gallium or heavy water, to provide a uniform material that's somewhat susceptible to interacting with neutrinos. And so this material would be placed deep underground because cosmic rays can cause interactions in the material, just like the neutrinos. And so the Earth itself has to be used as a shield. Cosmic rays are high-energy particles that stream from galactic space and impact the Earth's atmosphere. They create showers of high-energy particles in so doing that then decay into neutrinos. This is a source of noise that needs to be removed by going deep underground. Now, it's not a surprise that experiments have detected them, and it's well understood today that they have. So I know this is giving away the story at the beginning, but just getting neutrinos that come directionally from the sun and have the calculated energies gives us extreme confidence that fusion is happening in the sun's core. So let's look at some of the experiments that went on this epic hunt. The first really important neutrino detector was the Homestake Mine neutrino detector. It was designed by Raymond Davis, and John Bacall provided the theoretical background. And it was founded basically on Pontecorvo's reaction that he had discovered in 1945. This was Bruno's big idea for a big experiment. And Davis and Bacall ran this from 1970 through 1994. It was located in an old gold mine in Lead, South Dakota, about a mile underground, and that shielded it from the cosmic rays. Davis's experiment filled this 100,000-gallon tank with dry cleaning fluid, which contained the chlorine needed. Some of the chlorine in the solution would extremely rarely react with an incoming neutrino to form argon-37. Now, this reaction has a threshold energy of about 800 kiloelectron volts, so the Homestake Mine detector was sensitive only to solar electron neutrinos from the proton-proton chain and couldn't detect any other neutrino flavors. To measure the reactions, every 3 months, the carrier argon, which is argon-36, and any additional argon-37 that was produced during the run were removed from the detector by bubbling it through with some helium gas. So they had to pump the whole thing out. The argon was then purified with gas chromatography and pumped into a proportional counter. They then counted all the individual atoms of argon-36 and argon-37, those two isotopes. This then counted the total number of neutrinos that had interacted with the chlorine. This is an incredible undertaking, but what they found was very weird. For 22 years of running the experiment, Davis's team always only found 1/3 of the neutrinos that were expected from Bacall's predictions using the standard solar models. Where were the other 2/3 of the expected neutrinos? So therefore, the theoretical background, well, Bacall thought it was complete, and the first response from the scientific community was either that Bacall or Davis had made some sort of epic mistake. Bacall's calculations, we checked them repeatedly, have other people check them, and no errors were found. Davis scrutinized and went over his experiment, and he insisted there was nothing wrong with it. And Bacall was stunned by this, and he went round and round trying to figure out what the heck was the issue. It was this discrepancy that created the solar neutrino problem and spurred other experiments along to solve it. And since this isn't a murder mystery, Davis was eventually vindicated and co-awarded the Nobel Prize in 2002. During the time that the Homestake Mine was making its detection runs, physicists Stanislav Mikheyev, Alexei Smirnov, and Lincoln Wolfenstein developed the idea that neutrinos could transform into each other much more easily in the presence of matter. In this way, as they traveled out the sun's bulk, they would transform from one flavor into another, and this provided a possible avenue to solve the discrepancy found by the Homestake experiment. And specifically, the dates were in 1978 and 79. Lincoln Wolfenstein found that the oscillation parameters of the neutrinos are changed while in the presence of matter. And in 1985, the Soviet physicists Mikhailov and Smirnov predicted that a slowly decreasing gradient in the density of matter would resonantly enhance this mixing that Wolfenstein discovered. And Pontecorvo looked on since he posited decades before that this might be the case. And he passed away in 1993, but his contributions are recognized by the community and critical insights and advancements. Now, the exact mechanism for the MSW effect, named after Mikhailov, Smirnov, and Wolfenstein, has to do with the weak nuclear force and its very short range of effect, and the density of electrons. The higher the density of electrons, the greater the effect. Remember that neutrinos don't interact via electromagnetism or the strong nuclear force, only the weak nuclear force and gravity. This MSW effect shows that there's a small chance that the neutrino does make the change, but it needs to pass through a lot of matter and specifically a lot of electrons to do so. But the sun's got that covered. The huge mass of the sun provides an ample opportunity for the neutrinos to make the change from one flavor to another. Yep, that's what they're called, flavors. You can thank UC Berkeley for that. And the MSW effect has been confirmed for cosmic rays passing through the Earth, and the effect is a real one. Further, supernova 1987A's neutrino counts in the various experiments across the globe could be understood only if the MSW effect was taken into account, as the neutrinos pass through the Earth at differing depths. So notice it was really only completed in 1985, and 2 years later, here's the supernova that could test this idea. That's amazing. Now, to understand how the problem was solved, we need to know what an experiment might look like with a different kind of detector. If you've ever seen photos of a nuclear reactor, like this one, you might notice a blue glow surrounding the core. This phenomenon is called Cherenkov radiation, and it's a shock wave of light. Cherenkov radiation was first discovered in 1934 by the physicist Pavel Cherenkov from Russia. From Russia. Now, Cherenkov radiation happens when electrically charged particles, like electrons, travel faster than the speed of light in a clear medium such as water. And when an electron or neutron travels through the water at this high speed, it interacts with the atoms of the water molecules to give off light. This all happens because the speed of light in water is about 75% of the speed of light in a vacuum, which allows for the possibility of particles emitted from nuclear fuel to move faster than the speed of light as light goes in water. And they actually do. As this charged particles disrupt the water molecules in their path, photons are released, and it creates a visible shock wave of blue-violet light. This is similar to a sonic boom when objects move faster than the speed of sound. And in fact, brain cancer patients have seen these flashes of bright blue light in their eyes when receiving radiation treatments. That too is Cherenkov radiation. So here's how it works. When a neutrino enters a huge tank of pure heavy water, the neutrino might hit an electron in some atom, and that causes a recoil action. It'll be like a billiard ball that's going almost the speed of light. When it whacks the electron would then be ionized from the atom and speed away with a huge amount of energy. Now, if this speeding electron is moving inside a medium like water at faster than the speed of light in water, you get the Cherenkov radiation. It's just like as in sonic booms and bow shocks, the angle of the shock cone is directly related to the velocity of the disruption. So the radiation makes a cone shape, but there's a minimum energy to make this kind of radiation. And the Cherenkov angle is 0, meaning at this threshold velocity, meaning it's a dot or a point. The angle of the cone takes a maximum as the particle speed approaches the speed of light in a vacuum, in excess of the speed of light in the water. Hence, the observed angles of incidence can be used to compute the direction, speed, and energy of a Cherenkov radiation-producing charge. Another way to make the radiation is for the neutrino to cause a nuclear reaction, which transforms a nucleon into other particles, and specifically, an electron bursts out of the nucleus at high speeds to create the light. Let's look at one of the experiments that did this. The Kamiokande experiment was started in 1983, and it was a cylindrical tank, about 3,000 tons of pure water, and had 1,000 photomultiplier tubes attached to the inner surface of this. And the height of the detector was about 16 meters, and it was about 15 meters in diameter. And this was hunting for, specifically it was created to hunt for proton decay, and that was the physics goal of it. The upgrade to this project was the Super Kamiokande, and it started operation in 1996. Super Kamiokande neutrino detector was also a big stainless steel tank like this, but it was almost 40 meters in diameter and 40 meters tall, and was filled with 50,000 tons of ultra-pure water, and there were about 13,000 photomultiplier tubes installed all along the tank walls. So the detector is, of course, located a kilometer underground in a mine called the Mizumi mine near the city of Hida in Japan. And what you see here pictured is the interior of the Super Kamiokande detector. And so all of those balls on the wall, those are the photomultiplier tubes surrounded by a glass ball. And of course, you got to go in and do maintenance, and that's why the guys are in there in a raft. This experiment could tell the energy differences between the low-energy neutrinos that were coming from the sun and the high-energy ones that were coming from cosmic rays that hit the Earth's atmosphere. And they were fewer high-energy neutrinos towards the center of the Earth. And that means those neutrinos were being transformed as they passed through the Earth. And so the MSW effect was real for these cosmic ray neutrinos. So not only did the Kamiokande experiment confirm this neutrino problem and the fact that the light, because of the Cherenkov light made a cone, they showed the direction of the origin. And this proved that neutrinos were indeed coming from the sun. Using the timing and charge information recorded by each photomultiplier tube, and where the point was the interaction vertex, meaning that in this image we see here, this ring of detection and the flavor of the incoming neutrino could be determined. From the sharpness of the edge of the ring, the type of particle can be inferred. The multiple scattering events of electrons, there's a bunch of them and they're large, so electromagnetic showers produce fuzzy rings. But highly relativistic muons, in contrast, they travel almost straight through the detector and produce rings with very sharp edges. So that's how they can detect the difference between a muon neutrino and an electron neutrino. So they announced the first evidence of neutrino oscillation in 1998. And this was the first experimental observation supporting the theory that neutrinos had non-zero masses, and a possibility that people had been speculating about for years. But the design of the experiment was to detect proton decays and not explicitly these solar neutrinos, so its results were really compelling, but they weren't the final word. Just for amusement, it's such an amazing view. Here's another view of the interior of the Super Kamiokande detector. Look at this. Look at how pure that water is, because this is a cylinder, not a sphere. So we're looking at some amazing, amazing work that's going on through this thing. And I can't even tell where the bottom of the pool, the tank is, and where the walls are. It's almost impossible to tell from this image. Also, I'm sure that they have to be extremely careful about what tools they take in there, because you drop a hammer, you break that thing, and then you got to drain all the glass, all the water out, and pick out all the glass and repair something. So I'm sure that you have to be a very special sort of someone to be in that raft going around doing the cleaning and inspection. The final critical experiment, the Sudbury Neutrino Observatory, used heavy water, where one of the atoms of the hydrogen is deuterium, and that was used to detect all three flavors of neutrino. This detector was turned on in May of 1999, and it ran until the end of 2006. It was run in two modes of detection, one for electron neutrinos and the second for all three types of neutrinos. And the first scientific results were published in summer of 2001. And this presented the first clear evidence that neutrinos oscillate. That means they transmute from one to the other as they travel from the sun. The oscillation also then implies that neutrinos have non-zero masses. And those non-zero masses are listed in the little boxes above because mass is equal, well, remember from Einstein's equation, E equals mc squared. The energy is either in the form of mega electron volts or electron volts. And if you divide it by c squared, you get a mass. So this is fairly typical for particle physics to quote masses in this way, like electron volts per c squared or mega electron volts per c squared. And notice these are upper limits. So the lower limit, or the exact measurement of the mass of the neutrinos, they know an upper limit, but they don't know a lower limit. They don't know how tiny it could be, but they know it has to be less than this, and it has to be some mass. So the total flux of all the neutrinos that were measured by the Sudbury Neutrino Observatory agreed with all the theoretical predictions. And though the Super Kamiokande had beat the SNO to the publication, and they published some of their oscillation evidence in 1998, the Super Kamiokande results were not as conclusive and did not specifically deal with solar neutrinos. The Sudbury Neutrino Observatory were the first to directly measure the oscillations for all three types because it could be run in those two modes. One mode just looking only for the electron neutrino and one looking for all three. So this was incredibly important because it supported the evidence for the standard solar model. As neutrinos streamed out of the sun, this neutrino observatory was able to see that yes, they were coming from the sun, and they were that they had the right energies for each of the different kinds of neutrinos. So the validation that nuclear fusion happens in the sun and the standard solar model is a real thing. This was such an important development that in 2015, the Nobel Prize for Physics was awarded to Arthur McDonald of the Sudbury Neutrino Observatory and Takaki Kajita of Tokyo for the discovery of these oscillations. And these teams showed that the neutrinos do indeed transform and that all the neutrinos are there when the MSW effect is taken into account. And this solves the riddle, the solar neutrino problem that was posed by the Homestake mine. So, neutrinos have been discovered. And this amazing back and forth between theoretical ideas and experiments that were devised to test those hypotheses is a testament of the robustness of the scientific process. And even the big scare that Davis and Bacall had with their experiment was critical for this advancement, since they put out their results to encourage others to either help them or find where they went wrong. In the end, they didn't do anything wrong, but they weren't able to take into account the MSW effect until it had been devised. And in fact, the Homestake mine couldn't detect the other two neutrinos anyway. Hans Bethe's concept about the proton-proton chain was written quite soon after the discovery of the electron neutrino, but he couldn't have included the neutrino oscillation because the idea hadn't been developed yet. It is this adaptation to the shifting understanding and advancement of knowledge that is the hallmark of great science. It wasn't that, oh, there's 2/3 of the neutrinos. We know there should be there, but we just might have something wrong with our experiment. Maybe there's something wrong with our calculations. What did we do wrong? And so other people came along and did other tests to see if that could be true. And they were vindicated. The neutrino observatories fundamentally directly measured the processes that were happening in the center of the sun. And the Homestake mine was measuring them, but they just weren't sensitive to these other energies, these other higher energy neutrinos. That's amazing. So now that we know that nuclear fusion actually happens in the sun, and therefore in other stars, What happens when the star, or the sun, runs out of hydrogen in the core to fuse? And that's a really good question, and we'll get into that next time. I do hope you enjoyed this video. I want you, please subscribe and like this video. And I wanted to say a big thanks to my Patreon supporters who, without their help, this would be very difficult. So thank you all to my Patreon supporters, and we'll see you next time.